Hello there and welcome to Physics with William, where curiosity gets cozy, the universe gets a little quieter, and the strangest ideas in physics are allowed to stretch out comfortably before bedtime. Tonight, we're going to wander toward one of the most extreme edges of nature, not the edge of a galaxy, not the edge of a black hole, and not even the edge of time itself, but the edge of motion, in a sense so deep that ordinary language begins to creak a little. Our subject is Planck momentum, sometimes described as the greatest amount of momentum that can meaningfully fit inside the known rules of physics before those rules start asking for a chair and a glass of water. Momentum is one of those words that sounds familiar because we use it outside physics all the time. A football team has momentum when the match starts turning in its favour. A busy week has momentum when one appointment pulls you into the next. Even a sleepy thought can have momentum drifting gently from one idea to another until you realise you have been staring at the ceiling for several minutes and thinking about whether penguins have knees. But in physics, momentum has a more precise meaning. It is connected to how hard it is to stop something that is moving. A slow-moving bicycle has some momentum. A fast-moving train has much more. A tiny particle racing near the speed of light can carry a surprising amount. Momentum is not just motion. It is motion with consequence. It is motion that says, if you want to change me, you will need to deal with what I am bringing along. Planck momentum takes that familiar idea and carries it to a place where it no longer feels familiar at all. It belongs to the Planck scale, that strange region of physics where the smallest lengths, the shortest times, the greatest energies, and the strongest gravitational effects all seem to crowd together. It is the scale named after Max Planck, the physicist whose work helped open the door to quantum theory. And like many doors in physics, once it opened, everyone immediately realised the room behind it was much larger and much stranger than expected. Planck momentum is not something you meet in daily life. It is not hiding in your morning coffee, unless your coffee is moving with such violent intensity that it has become a threat to space and time, in which case I would gently suggest switching brands. It is not the momentum of a thrown ball, a speeding aircraft, or even a particle in our most powerful accelerators. It is far beyond those. It is a natural scale, built from some of the deepest ingredients in physics, and it points toward a boundary where quantum mechanics, gravity and relativity all begin to speak at once. Before we go further, let me ask you something simple and fitting. Where are you listening from tonight, and what is moving around you right now? Maybe you can hear a car passing outside. Maybe there is wind at the window, a clock ticking nearby, or the quiet shifting of a blanket as you settle in. Perhaps everything seems still, but even then, you're sitting on a rotating planet, orbiting a star, carried with that star around the Milky Way, while the Milky Way itself moves through the cosmic dark. Stillness, in physics, is often just motion viewed politely from the right seat. So wherever you are, and however calm the room feels, you're already part of an enormous moving system. A gentle one, from your point of view. Thankfully. But moving all the same. If you find this kind of quiet journey soothing, if it helps you relax while still giving the mind something interesting to hold, I would be very grateful if you liked the video and subscribed. It helps this calm little corner of science reach other people who may also enjoy drifting off while the universe explains itself in its own peculiar way. And do feel free to share where you are listening from. The topic about momentum feels especially fitting when the listeners themselves are scattered across a turning Earth, each carried through space at speeds we almost never notice. To begin this story, it helps to start not at the Planck scale, but with something much more ordinary. Imagine a pebble resting in your hand. It is still relative to you. You can feel its weight. You can toss it gently upward and catch it again. When it moves, it has momentum. If you throw it softly, it is easy to stop. If someone throws a heavier stone faster, it becomes harder to stop. That is the everyday intuition behind momentum. It combines how much stuff is moving with how quickly that stuff is moving. Heavy and fast means more momentum. Light and slow means less. Simple enough for a garden, a cricket pitch, or a slightly overconfident child with a snowball. But nature has a habit of taking simple ideas and asking how far they can go. What happens if something moves faster and faster? What happens if the object becomes smaller and smaller? What happens if we stop talking about pebbles and start talking about particles, beams of light, or matter squeezed into spaces so tiny that even atoms seem enormous by comparison? Momentum does not disappear. It becomes more important. At very small scales, momentum is tied to quantum behavior. Particles are not just little beads flying through emptiness. They have wave-like properties. They can be spread out in probability. The more sharply you try to pin down where something is, the more uncertain its momentum becomes. The smaller the space you force a particle into, the more violently its possible motion seems to respond. It is as if the universe has a built-in reluctance to let anything be confined too neatly. Try to trap it in a tiny box, and motion begins to push back. At the same time, if you pack enough energy or momentum into a small enough region, gravity cannot be ignored. This is where the story becomes more serious. Gravity is usually weak in the world of particles. A fridge magnet can lift a paperclip against the pull of the entire Earth, which is a slightly embarrassing performance for gravity when you think about it. But gravity becomes powerful when energy is concentrated. Energy and momentum affect the shape of space and time. They are not just passengers in the universe. They help tell the universe how to curve. And if too much is concentrated too tightly, the result may no longer be a particle in the usual sense. It may begin to resemble a black hole. That is one reason the Planck scale is so interesting. It is where the quantum tendency to become uncertain and restless meets the gravitational tendency to curve space and time. In ordinary physics, we often use different theories for different jobs. Quantum mechanics handles atoms and particles. General relativity handles gravity, stars, planets, and black holes. Most of the time, this division works beautifully. It is a little like using a teaspoon for tea and a ladder for cleaning the top shelf. Both are useful. You would not normally confuse them, but at the Planck scale, the teaspoon and ladder somehow have to solve the same problem, and no one is entirely sure what the correct combined tool looks like. Planck momentum sits at this meeting point. It is not just a large momentum. It is the momentum scale suggested by combining the constants that govern quantum behavior, gravity, and the speed limit of the universe. These constants are not random decorations in physics. They are more like load-bearing beams. One tells us about the quantum graininess of nature. One tells us about gravity. One tells us the speed at which light travels in empty space, and more broadly, the speed limit for cause and effect. When those ingredients are blended in the right conceptual way, a family of Planck quantities appears. Planck length, Planck time, Planck mass, Planck energy, and Planck momentum. Each one points to an extreme natural scale. Not a scale we have reached in experiments, but one that appears again and again when asking where our present theories might stop being enough. Calling Planck momentum the maximum momentum possible is tempting, and in many ways useful for setting the mood. But as with many tempting phrases in physics, we should hold it gently rather than gripping it too tightly. Physics is careful about what it claims. Planck momentum is often treated as a natural upper scale where our familiar descriptions may break down. That does not automatically mean there is a proven universal speed bump with a sign saying no momentum beyond this point. The universe is rarely so considerate with signage. Instead, Planck momentum tells us that if a single object, particle, or physical process were associated with momentum around that scale, we would likely need a theory of quantum gravity to describe it properly. Our current maps would begin to blur. The roads might still continue, but the street names would be missing. This distinction matters because physics is not only a collection of answers, it is a discipline of careful questions. When we say maximum momentum, we're really asking what it would mean for momentum to become so large that trying to measure it, localize it, or assign it to a familiar object causes the concepts themselves to strain. If a particle had an incredibly high momentum, it would also have an incredibly short associated wavelength. That would suggest it could probe extremely tiny distances, but probing tiny distances requires concentrating energy. Concentrating energy invites gravity. At some point, the act of trying to see smaller and smaller may create the very thing that hides what you're trying to see. The microscope turns into a curtain. Push hard enough into the small, and nature may answer not with a clearer image, but with a horizon. A horizon, in this sense, means a boundary like the one around a black hole, beyond which information cannot easily return to an outside observer. That is a remarkable thought. We usually imagine that more energy gives us sharper tools, better microscopes, faster particle beams, finer detail. For much of science, that has been true, but the Planck scale hints at a reversal. More momentum may not mean more access. Beyond a certain point, it may mean collapse, concealment, or a new regime where space itself is no longer smooth enough to be treated like a stage. It is as though the universe lets us zoom in only so far before the picture stops being a picture and becomes the material of the screen. This is why Planck momentum is not merely a number for specialists to place in a table. It is a clue. It points toward the unresolved border between the physics we know and the physics we are still trying to build. Somewhere around that border, the ordinary idea of a particle moving through space may not be the right language. The idea of position may change. The idea of distance may change. Time may not behave in the usual way. Even momentum itself may need to be understood differently. That is not because scientists enjoy making things difficult, although to be fair, some equations do give that impression. It is because nature has shown us that familiar concepts are often local habits, not eternal guarantees. What works in a kitchen, a laboratory, or even near a star may not work at the smallest and most energetic frontier. For tonight, though, we do not need to rush into the deepest mathematical forest. We can approach Planck momentum slowly, the way one approaches a dark shoreline at night, listening first to the water before trying to map the coast. We will start with the everyday meaning of momentum and then widen it. We will see why motion is not just about speed, why mass and energy complicate the story, and why light, despite having no ordinary rest mass, still carries momentum. We will meet Max Planck and the strange revolution that began when physicists realized energy did not always behave like a smooth-flowing stream. We will look at why the Planck scale appears when quantum theory and gravity are forced into the same room, and gradually, without formulas and without demanding too much of a tired mind, we will see why Planck momentum is treated as a kind of natural extreme, a marker for the place where known physics begins to whisper, "This is as far as I can guide you for now." There is something comforting about this kind of limit. Not because it closes the universe down, but because it gives shape to the unknown. Humans have always used boundaries to think. The horizon tells us where the visible sea ends, even though the ocean continues beyond it. The edge of a map tells us where the map maker stopped, not necessarily where the land stopped. Planck momentum is like that. It is not necessarily the end of reality. It is the edge of one of our maps. It says that motion, energy, space, time, and gravity cannot be pushed indefinitely through the same old concepts without something changing. And that is a very useful thing to know. A boundary is not just a wall. Sometimes it is an invitation to build a better doorway. It also reminds us that the universe is not built around human scale. Our instincts were shaped by stones, animals, rivers, weather, and walking speeds. We understand momentum most naturally when something bumps into something else. A rolling cart, a falling apple, a door pushed too enthusiastically. The Planck scale is almost absurdly far from that world. It is so far beyond ordinary experience that our metaphors start wearing thin shoes. Yet the same universe contains both. The gentle motion of your breathing and the possible maximum momentum scale of nature are not separate realities. They are connected by laws that somehow describe falling rain, orbiting moons, atomic transitions, and the hidden violence of black holes. That unity is one of the reasons physics can feel peaceful even when the subject is extreme. It suggests that reality, for all its strangeness, is not a pile of unrelated facts. It is more like a single piece of music played across a range far wider than we can hear at once. As we settle into this topic, it may help to keep one simple picture in mind. Momentum is nature's way of giving motion a kind of persistence. A moving thing carries a tendency to keep moving unless something interacts with it. The larger the momentum, the more serious that tendency becomes. Planck momentum asks what happens when that seriousness becomes cosmic, when the persistence of motion is no longer just enough to knock over a cup or steer a spacecraft, but enough to challenge the structure of space and time. It is motion brought to the threshold where our best theories stop behaving like separate tools and start demanding a deeper explanation. So let the room stay quiet for a moment. Let the ordinary motions around you remain ordinary. The soft rise and fall of breath, the tiny adjustments of the body, the distant traffic, the slow turning of Earth beneath the night. All of these have momentum in their own way. None of them require quantum gravity to understand, which is fortunate because nobody wants to calculate a blanket at bedtime. But from these gentle motions, we can begin walking toward the most extreme motion scale physics can name, and along the way, the humble idea of momentum will become a guide into some of the deepest questions we have. To understand why Planck momentum matters, we first need to give momentum itself a little more attention than it usually gets. Not too much at once, not in the manner of a chalkboard ambush, but enough to feel how the idea works before we stretch it toward the edge of known physics. Momentum begins in the simple observation that moving things resist changes to their motion, and that resistance depends not only on how fast they move, but on what they are. A feather drifting across a room and a bowling ball rolling at the same speed are not equally persuasive if they meet your foot. One is a mild interruption, the other is a lesson. From there, the story of Planck momentum begins its long climb, because the universe does not reserve momentum only for objects we can hold. It gives momentum to particles, to light, to fields, and to processes so energetic that the difference between motion and gravity begins to blur. To understand Planck momentum, we first have to become comfortable with ordinary momentum, which sounds easy, until we notice that ordinary momentum is already a little stranger than it appears. It is one of those ideas that hides in plain sight. You can feel it when a shopping trolley refuses to stop cleanly at the end of an aisle. You can feel it when a train glides into a station with such calm heaviness that it seems impossible anything could ever truly hurry it. You can feel it when you catch a ball and your hands move backward without asking permission, because your body knows that stopping motion is not just about touching it. Stopping motion means accepting what that motion is carrying. At the simplest level, momentum is the stubbornness of motion. A moving thing has a tendency to keep going, and the more momentum it has, the more effort is needed to slow it, stop it, turn it, or send it back the other way. A small stone tossed gently across a pond has a little momentum. A lorry moving down a hill has a great deal more. A dust grain drifting in sunlight has so little that a warm air current can redirect it without ceremony. Momentum is not just speed, and it is not just size. It is what happens when the amount of matter in an object and the way that matter is moving are considered together. That is why a slow, heavy object can still be difficult to stop, and a fast, light object can become surprisingly forceful. Momentum is motion with weight behind it, although in modern physics we have to say that carefully, because weight and mass are not quite the same thing, and physics does enjoy placing small traps under familiar words. Imagine standing beside a frozen pond and sliding two objects across the ice. One is a small wooden block, the other is a heavy metal weight. If both glide at the same gentle speed, the metal weight is harder to stop. It carries more momentum because there is more matter moving. Now imagine two identical wooden blocks, one sliding lazily, the other racing across the ice. The faster one is harder to stop because its motion is more intense. Momentum grows when there is more stuff in motion, and it grows when that stuff moves faster. This basic idea is so useful that it sits at the heart of mechanics, the branch of physics that studies motion, forces, and the way objects respond when they meet the rest of the universe. But momentum is not only about how much motion something has, it also has direction. A bicycle moving north and an identical bicycle moving south at the same speed do not have the same momentum, because they are carrying their motion in opposite directions. This matters enormously. If two skaters push away from each other on ice, one goes left and the other goes right. Their motions balance in a way that preserves the total momentum of the pair. If two balls collide on a billiard table, the motion does not simply vanish when they touch, it is redistributed. One ball slows, another speeds up, directions change, and the total account of momentum is carefully kept, even if the balls themselves look as if they are improvising. This brings us to one of the deepest and most calming facts about momentum. In an isolated system, total momentum is conserved. That means it does not simply appear from nowhere or disappear into nothing. It can move around. It can pass from one object to another. It can hide in directions that cancel. It can spread through a crowd of particles. But the total stays balanced. Nature keeps the books. Not in a dramatic way, not with thunder and cosmic paperwork, but quietly, with a reliability that allows planets to orbit, rockets to fly, atoms to collide, and billiard players to blame the table. Conservation of momentum is one reason physics can make predictions. If you know the momentum before a collision, and you understand the forces involved, you can work out what must happen after. A cannon fires a cannonball forward, and the cannon rolls backward. A swimmer pushes water behind them and their body moves forward. A rocket throws hot gas downward and backward, and the rocket rises upward and forward. Nothing magical needs to pull the rocket into the sky. It climbs because momentum is being exchanged. The exhaust carries motion one way, the rocket carries motion the other. The same principle works whether you're launching a spacecraft or accidentally pushing yourself away from a desk on a wheeled chair while trying to look professional. Momentum is so fundamental because it is tied to the symmetry of space itself. That may sound grand, but the idea is gentle enough. The laws of physics do not seem to care where in empty space you perform an experiment. A collision here follows the same basic rules as a collision over there, provided the conditions are the same. Because space has this sameness from place to place, momentum is conserved. This connection between symmetry and conservation is one of the great insights of modern physics. When nature has a kind of sameness, something is protected. Momentum is protected because space is, in a deep sense, uniform. It does not have a preferred location where motion rules suddenly change. The universe may be full of stars, dust, people, and badly placed coffee tables, but the underlying laws do not treat one empty region of space as more special than another. This is already a clue that momentum is more than a schoolroom quantity. It is woven into the structure of physical law. It is not just a convenient way to describe a moving cart. It is linked to the way space behaves, and when an idea is that deeply connected, it tends to survive even when physics becomes strange. Momentum remains important in relativity, in quantum mechanics, in particle physics, and in the early universe. It changes its clothing as it moves between theories, but it does not leave the room. In everyday life, we often separate energy and momentum as if they are different characters. Energy is what lets something do work. Momentum is what makes motion hard to change. But at deeper levels, they are closely related. A moving object has energy because of its motion, and it has momentum because of its motion. The two are not identical, but they travel together. Push an object harder and both its energy and its momentum can increase. Heat a gas, and the molecules inside move more vigorously, carrying more momentum in all directions, bumping into the walls of their container more often and more forcefully. Fire a particle through an accelerator, and its energy and momentum become part of the same relativistic story. A story in which speed, mass, and the speed limit of nature all have to be treated with care. This is where our everyday intuition begins to loosen. In the ordinary world, if you keep pushing something, it speeds up. A trolley, a bicycle, or a sled can all be made faster by applying force. You might imagine that if you could keep pushing forever, the object would eventually move as fast as you liked. But relativity tells us that nature has a speed limit. Massive objects cannot be accelerated to the speed of light. As they move faster and faster, adding energy does not produce the same simple increase in speed. Instead, the object gains more energy and more momentum while its speed approaches the cosmic limit without reaching it. It is a little like trying to reach the end of a hallway that keeps stretching just enough to remain ahead of you. You can make progress, you can get closer, but the limit stays beyond touch. This means that at very high speeds, momentum can become enormous even when speed changes only slightly. The object is not racing past the speed of light. It is carrying more and more energy and momentum as it approaches that boundary. This is one reason particle accelerators are so powerful and so difficult. They do not simply make particles fast in the casual sense. They give particles huge amounts of energy and momentum, squeezing extraordinary physical significance into incredibly small travelers. When those particles collide, their momentum and energy can transform into new particles, radiation, and patterns that reveal the hidden structure of matter. The collision is not just a crash. It is a question asked very sharply. Light complicates the story in another beautiful way. A beam of light has no ordinary rest mass, yet it carries momentum. You can see this in subtle effects. Light can push, very gently but truly. The pressure of sunlight can nudge dust in space and can in principle propel a solar sail. This seems odd if we only think of momentum as belonging to heavy objects, but modern physics tells us that momentum belongs not only to matter with rest mass, it belongs to energy moving through space. Light carries energy, and because it travels, it carries momentum as well. A photon, the quantum of light, is not a tiny billiard ball in the old-fashioned sense, but it still has directional motion that can be exchanged. When light strikes a surface, it can transfer momentum. Tiny, tiny amounts, yes, but real enough that spacecraft designers and astronomers must take it seriously. This matters for Planck momentum because the deepest version of momentum is not tied only to lumps of matter. It is tied to motion, energy, direction, and the structure of space-time. When we move toward extreme physics, we cannot rely only on pictures of balls and carts. We need a broader idea, one that includes particles, radiation, fields, and perhaps even the geometry of the universe itself. Momentum becomes part of the language that tells matter and energy how to move, and tells space and time what is happening inside them. Now let us shrink the scene. Instead of trains and stones, imagine particles. Not tiny balls exactly, though that image can be useful for a moment, but quantum objects whose behaviour is described through probabilities. In quantum mechanics, momentum becomes linked to wavelength. A particle with greater momentum has a shorter associated wavelength. That matters, because wavelength is related to how finely a particle can probe the world. If you want to investigate smaller structures, you need shorter wavelengths, which means higher momentum. This is why particle accelerators are also microscopes of a special kind. They do not use glass lenses. They use high momentum particles to examine distances far smaller than anything visible light could resolve. There is a catch, of course. Physics is full of catches. At first, the strategy works wonderfully. Increase the momentum, shorten the wavelength, see smaller details. This approach helped reveal the structure of atoms, then nuclei, then the particles inside protons and neutrons. It allowed scientists to explore the deep architecture of matter. But if we keep imagining greater and greater momentum, eventually we approach a point where gravity becomes impossible to ignore. This is strange because gravity is usually irrelevant for tiny particles. The gravitational pull between two small particles is unbelievably weak compared with the electric and nuclear forces. But high momentum means high energy, and energy gravitates. Concentrate enough of it into a small enough region, and the geometry of space-time begins to respond. Here, the universe starts whispering that the old approach may not continue forever. If you try to probe a very tiny distance by using a particle with tremendously high momentum, you also concentrate energy into that tiny region. But energy can curve space-time. Push the experiment far enough, and instead of seeing a smaller detail, you may create conditions where a tiny black hole forms. The very act of looking more closely could hide the thing you wanted to see. It is like bringing a brighter and brighter lantern into a delicate fog, only to find that beyond some brightness the fog catches fire and becomes the main event. The tool changes the situation so strongly that the original question has to be reconsidered. This is one of the ideas behind the significance of the Planck scale. Planck momentum is associated with the point where the momentum needed to probe fantastically. Small distances become so extreme that quantum effects and gravitational effects can no longer be separated. Below ordinary scales, quantum mechanics rules. Around massive bodies, general relativity rules. But when extremely high momentum is packed into extremely tiny distances, both theories demand attention at once. The result is not simply difficult, it is conceptually unfinished. We do not yet have a fully confirmed theory that unites quantum mechanics and gravity in this regime. We have promising approaches, serious proposals, and many brilliant arguments, but not a final tested map. That is why Planck momentum should be understood with care. It is not like the maximum speed limit set by relativity, where the speed of light in empty space plays a clear and experimentally confirmed role. Planck momentum is a natural scale. It signals a boundary of meaning within our current theories. If a particle or process reaches momentum around that scale, our ordinary descriptions may no longer be reliable. It may be misleading to talk about a point particle simply moving through a smooth space-time. The space-time itself may fluctuate. The idea of distance may become uncertain. The object being measured, the measuring process, and the geometry around them may no longer be cleanly separated. At that level, physics may need new words, not just larger numbers. The phrase maximum momentum possible is therefore both exciting and slightly dangerous. It gives us a vivid picture, but it can sound more settled than the science really is. A careful physicist might say that Planck momentum is the largest momentum scale that can be formed naturally from the constants governing quantum theory, gravity, and relativity. It is where we expect quantum gravity to become important. It may represent a meaningful upper limit in some theories, especially those that suggest space-time has a smallest possible scale, or that ordinary momentum cannot grow without bound, but whether nature absolutely forbids any form of momentum beyond it is not something we can claim from direct experiment. Our accelerators are nowhere near that realm. The early universe may have approached it, and black hole physics may hint at it, but we cannot yet place Planck momentum on a laboratory bench and ask it to behave. Still, even as a natural scale, it is profoundly useful. Physics often advances by identifying the scales at which old assumptions fail. The speed of light revealed that Newtonian ideas of space and time were not the whole story. The quantum of action revealed that energy and measurement at small scales did not behave as classical physics expected. The Planck scale tells us that our two greatest modern frameworks, quantum theory and general relativity, are both pointing toward a region where neither can stand alone. Planck momentum is one of the signposts at that border. It says that motion, when compressed into its most extreme meaningful form, may become indistinguishable from questions about the structure of reality itself. There is also a quieter lesson here about measurement. Momentum is not just something an object has in isolation. It is something we infer, exchange, and measure through interactions. To know a particle's momentum, we must let it affect something else. It might leave a track, scatter from a target, curve in a magnetic field, or produce new particles in a collision. Measurement is a physical process. It is not a ghostly act of looking. At ordinary scales, this is easy to forget. A speed camera measures a car without noticeably changing the car. A bathroom scale measures your weight without launching you through the ceiling, ideally. But in quantum physics, and especially near extreme scales, measurement and disturbance become inseparable. To ask about very high momentum is also to ask what kind of interaction could reveal it, and what that interaction would do to spacetime. This makes Planck momentum feel less like a trophy at the end of a race, and more like a warning light on the dashboard of physical meaning. It tells us that beyond this region, the familiar dashboard may not be calibrated. The needles still move, but we're not sure what they mean. A particle with ordinary momentum can be described as moving through space. A particle with huge but still accessible momentum can be treated using relativistic quantum field theory. But near Planck momentum, the background through which the particle moves may no longer be a passive stage. It may become part of the drama. Space and time may respond so strongly that the distinction between actor and stage begins to fade. A useful way to picture this is to think of walking across a wooden floor. If you are light and the floor is sturdy, you can ignore the floor's response. It supports you without changing much. If something extremely heavy moves across it, the floor bends, creaks, maybe breaks. Now imagine that the floor is not wood, but space-time, and the walker is not a person, but concentrated energy and momentum. At low levels, space-time is smooth enough to treat as a background. At extreme levels, it bends and reacts. Near the Planck scale, the floor may not even be made of continuous boards in the way we imagined. It may have a deeper structure, or it may not be a structure in any ordinary sense at all. Momentum also teaches us that motion is relational. To say something is moving usually means it is moving relative to something else. A passenger sitting on a train may feel still, while a person on the platform sees the passenger rushing past. Momentum depends on the frame of reference, especially in relativity. Different observers can assign different momentum values to the same object depending on their motion relative to it. This raises a subtle question when we speak of maximum momentum. Maximum according to whom? In ordinary relativity, momentum can increase without a simple universal cap as observers change frames. But Planck momentum enters discussions where gravity and quantum structure may alter that familiar freedom. Some speculative theories suggest modifications to how momentum behaves at the higher scales, perhaps introducing invariant limits alongside the invariant speed of light. These ideas are not settled, but they show why Planck momentum is not merely a big version of a small concept. It presses on the foundations of how observers, measurements, and space-time relate to one another. At human scales, momentum is practical. Wear a seatbelt because momentum matters. Do not stand in front of a rolling piano because momentum is not interested in your optimism. Catch an egg gently by moving your hand with it, because increasing the stopping time reduces the force. These lessons are immediate and bodily. At cosmic and quantum scales, the same concept becomes a guide to hidden reality. Momentum helps describe how galaxies move, how particles scatter, how light pushes, how fields carry influence, and how the smallest distances might resist being examined. Few ideas travel so well from the kitchen to the edge of physics. Momentum is humble enough to explain a rolling marble, and deep enough to appear in the question of whether space itself has a smallest meaningful scale. So when we speak of Planck momentum, we are not abandoning ordinary momentum, we are following it to its most extreme implication. We begin with the simple fact that motion can be hard to change. We notice that nature conserves momentum with extraordinary care. We see that momentum belongs not only to heavy objects, but also to light and fields. We learn that at high speeds, momentum grows in ways that everyday intuition does not predict. We discover that greater momentum can probe smaller distances. Then finally we reach the whisper. If momentum becomes too great and too concentrated, gravity enters the quantum room. The act of probing may become an act of curving. The search for smaller distances may create horizons. The idea of motion may require a new theory of spacetime. This is the path from a rolling stone to Planck momentum, not a sudden jump, but a long tightening of the same idea. Motion becomes persistence. Persistence becomes conservation. Conservation becomes symmetry. Symmetry becomes a foundation of physical law. Then, at the edge, that foundation meets the unknown. The universe seems to say that momentum is real, measurable, and conserved, but also that at its most extreme, momentum cannot be fully understood apart from the shape and perhaps the quantum nature of space and time. That is why this topic is so fascinating. It is not just about asking how much motion something can have. It is about asking when motion becomes so intense that it stops being a property inside the universe and starts becoming a question about what the universe is made of. For now, let the idea rest in a simple form. Momentum is the carried insistence of motion. It is the reason moving things do not change their state without an exchange. It is passed between objects, shared in collisions, carried by light, amplified in accelerators, and protected by the deep sameness of space. As it grows larger and is packed into smaller regions, it becomes a doorway into more extreme physics. Near the Planck scale, that doorway does not open into a tidy room with familiar furniture. It opens into a place where quantum uncertainty, gravity, and the structure of space-time all have to be considered together. And to understand why Max Planck's name appears on that doorway, we have to turn toward the quiet revolution that began when physicists first realized that nature, at its smallest scales, does not always flow smoothly, but sometimes arrives in indivisible steps. That quiet revolution began in a room that looked nothing like a gateway to the deepest structure of reality. There were no black holes on the table, no particle accelerators humming under the floor, no dramatic crack in space and time opening beside the fireplace. There was simply a problem about heat and light, a problem so ordinary in appearance that it could have been hidden inside a glowing stove, a heated metal rod, or the warm red mouth of a kiln. Yet from that glow came one of the greatest turning points in physics. It began with Max Planck, a careful, disciplined German physicist who was not trying to overthrow the universe. He was trying to make sense of a stubborn calculation. Planck was not the sort of scientist who entered the story like a thunderstorm. He was orderly, serious, musical, precise, and by many accounts quite conservative in his scientific instincts. He loved the stability of classical physics. He admired the grand structure built by Newton, Maxwell, thermodynamics, and the physicists of the 19th century. To him, the laws of nature were not toys to be broken for entertainment. They were elegant, reliable, and deeply worthy of respect. That makes his role in the birth of quantum theory almost amusing in a gentle way. The man who helped loosen the floorboards of classical physics did so reluctantly, as if apologizing to the furniture while rearranging the entire house. The problem that drew him in was called blackbody radiation. The name sounds a little ominous, as though it belongs to a mysterious object floating at the edge of a starless galaxy, but the idea is much more practical. A black body in physics is an ideal object that absorbs all light falling on it and then emits radiation depending only on its temperature. Real objects are not perfect black bodies, but many things approximate the behavior well enough to make the concept useful. Heat a piece of iron, and it begins to glow dull red, then orange, then yellowish white as it gets hotter. The colour tells you something about the temperature. A warm stove gives off infrared radiation that your skin feels as heat. The sun, though certainly not a perfect laboratory object, radiates in a way that can be studied using similar ideas. So the question was simple to ask. How exactly does a hot object distribute its light across different colours and wavelengths? Physicists already knew a great deal about heat, energy, and electromagnetic radiation. James Clerk Maxwell had shown that light is an electromagnetic wave. Thermodynamics had given scientists powerful tools for understanding heat and energy. Experimentalists could measure the radiation coming from heated objects with impressive care. The data had a very definite shape. At each temperature, the emitted radiation rose, peaked, and then fell away. Hotter objects shifted the peak towards shorter wavelengths, which is why heated metal changes colour and why blue stars are hotter than red ones. The experiments were not the problem. Nature had provided the curve. The difficulty was that classical physics could not explain the whole curve correctly. At longer wavelengths, the classical predictions worked fairly well. But at shorter wavelengths, especially toward the ultraviolet region, the old theory went badly wrong. It predicted that a hot object should emit more and more energy at shorter and shorter wavelengths, without limit. That would mean an ordinary heated object should pour out an impossible amount of high-frequency radiation. Since ovens do not vaporize the kitchen with endless ultraviolet light every time someone bakes bread, something was clearly amiss. This failure became known as the ultraviolet catastrophe, which is one of the more dramatic names in physics and thankfully not a cooking instruction. Planck approached this problem with determination. He was not initially searching for a new philosophy of nature. He wanted a formula that matched the experimental data. He wanted order restored. He worked with the mathematics of heat and radiation, trying to find a way to reproduce the observed curve, and in doing so, he made a move that seemed at first like a technical trick. He assumed that the tiny oscillators in the walls of a heated cavity could exchange energy with radiation only in discrete amounts. Not continuously, as classical physics would have expected, but in little packets. Energy in this strange procedure came in steps. This was the tiny doorway. A small assumption, introduced almost reluctantly to make the calculation work, but it had enormous consequences. If energy could only be exchanged in discrete packets, then the infinite runaway predicted by classical physics at short wavelengths was cut off. The curve matched the data. The catastrophe was avoided. The stove could remain a stove and not a cosmic disaster in the pantry. At first, even Planck did not fully treat these packets as physically real, in the way later physicists would. He saw them as part of the calculation, a useful device. But the seed had been planted. The universe, at its smallest scales, might not be smooth in the way classical physics assumed. This is a difficult idea because our everyday senses are trained by continuity. Water seems to pour smoothly from a jug. A violin note seems to slide from one pitch to another. A dimmer switch seems to raise light gradually. Motion appears to flow. Heat appears to spread. Time appears to pass without grain. Classical physics reflected that experience. It treated many physical quantities as continuously variable. You could have a little more energy, then a little more, then a little more again, with no smallest step in between. Planck's work suggested that, at least in certain interactions, nature did not allow every possible amount. It allowed specific amounts. The steps might be unimaginably tiny, far too small to notice in daily life, but they were steps all the same. A useful comparison is money, though it is imperfect. You can pay in whole numbers of the smallest coin your currency allows. You cannot hand someone half of that coin in an ordinary transaction and expect the cashier to remain cheerful. Large purchases feel continuous because the smallest units are so small compared with the total. But beneath the smooth appearance, there are discrete increments. In quantum physics, energy exchange can behave in a somewhat similar way. At human scales, the steps are usually so fine that the world looks smooth. But at atomic scales, the steps matter. They are not bookkeeping conveniences, they shape reality. Planck's constant became the marker of this graininess. It is a number that sets the scale of quantum effects. We do not need to write it down to understand its importance. It tells us how large the quantum steps are. Because it is so small by ordinary standards, quantum effects are usually hidden in everyday life. A football does not visibly behave like a wave as it crosses a field. A spoon does not occupy a blur of possible draw locations unless someone else unloaded the dishwasher. But for electrons, atoms, photons, and other tiny systems, the Planck constant is not negligible. It is the rule that says the small world has its own habits. Once that doorway opened, others stepped through. Albert Einstein used the idea of energy packets to explain the photoelectric effect, where light striking a metal surface can release electrons. This work suggested that light itself, long understood as a wave, could also behave as if it arrived in particles, later called photons. Niels Bohr used quantum ideas to build a model of the atom in which electrons could occupy only certain allowed energy states. Louis de Broglie proposed that matter had wave-like properties. Erwin Schrödinger, Werner Heisenberg, Paul Dirac, and many others helped create quantum mechanics, a theory so successful that it underlies chemistry, electronics, lasers, medical imaging, and much of the modern world. And all of this, in one way or another, traces back to Planck's hesitant little step away from continuity. It is easy now to look back and see the beginning clearly, but at the time it was not obvious. Scientific revolutions rarely arrive wearing a badge. They often begin as fixes, puzzles, awkward exceptions, or small cracks in a trusted wall. Planck did not declare that classical physics was finished. He did not announce that reality was stranger than anyone had imagined. He found a way to solve a radiation problem by introducing discrete energy elements. The deeper meaning unfolded gradually. This is worth remembering because physics is not only made of grand leaps, sometimes it moves through careful discomfort. A theory works almost everywhere, then fails in one place. Someone patches the failure. The patch turns out to be a window. Through the window, an entirely new landscape appears. Planck's contribution matters for Planck momentum because the Planck scale is built from the same insight that nature has fundamental constants. These constants are not human inventions in the way centimeters or seconds are human conventions. They appear to belong to the structure of the physical world. The speed of light tells us about the relationship between space, time, and causality. The gravitational constant tells us how strongly mass and energy curve and attract. The Planck constant tells us how quantum behavior enters the world of action, energy, and measurement. When these constants are combined conceptually, they produce natural scales. Not scales chosen because they are convenient for human hands or clocks, but scales suggested by the universe itself. This is a remarkable shift in thinking. Human units are local and practical. A meter is useful because people need to measure rooms, roads, and laboratory benches. A second is useful because we need to coordinate meals, trains, and the occasional regrettable alarm. But Planck units are not based on human convenience. They are built from the constants that govern the deep behavior of reality. Planck length is not small because someone wanted a tiny ruler. It appears when quantum theory, gravity, and relativity are placed together. Planck time is not brief because a committee was feeling impatient. It emerges from the same constants. Planck mass, Planck energy, and Planck momentum belong to this family as well. They are the natural language of extreme physics. Planck himself introduced natural units in a way that reflected his search for universality. He recognized that by using fundamental constants, one could define units that would have meaning beyond any particular civilization, planet, or measuring tradition. A meter depends on human history. A foot depends rather suspiciously on feet. But a unit built from constants of nature would mean the same thing to any sufficiently advanced observer anywhere in the cosmos. If distant beings around another star studied physics deeply enough, they might not use our words, our clocks, or our tea schedules, but they would discover the same constants. They could build their own version of Planck units from the same ingredients. This gives the Planck scale a special kind of dignity. It is not provincial, it is cosmic. There is something quietly humbling about that. Our ordinary measurements are shaped by bodies and habits. We measure time in ways connected to Earth's rotation and orbit. We measure distance with units that have passed through royal decrees, metal bars, light travel, and laboratory definitions. We measure mass with conventions that have been refined over centuries. These systems are practical and powerful, but they carry human fingerprints. Planck units feel different. They are not designed for groceries or carpentry. Nobody says the sofa is several billion Planck lengths too far to the left, even if it is. But for thinking about the deepest boundaries of physics, these units are extraordinarily natural. Planck momentum enters as one member of this natural family. To understand why it appears, we need to see that momentum connects quantum behavior to scale. In quantum theory, high momentum is linked to short wavelength, and short wavelength is linked to the ability to probe small distances. Meanwhile, relativity connects energy and momentum in a unified way, especially when speeds become extreme. Gravity then tells us that energy and momentum are not merely carried through spacetime, they help shape spacetime. Bring the quantum, relativistic and gravitational ingredients together, and Planck momentum appears as the momentum scale at which all three aspects become impossible to ignore. This is the enormous physics hidden inside Planck's tiny doorway. A calculation about heated objects led to the Planck constant. The Planck constant helped define quantum theory. Quantum theory, when placed beside relativity and gravity, points toward Planck scales. And Planck momentum tells us about a regime where a particle's momentum would be so extreme that treating space-time as a smooth, passive background may no longer work. The path from glowing metal to quantum gravity is long, but it is not disconnected. It is one continuous line of thought, drawn through the history of physics by the question of how nature behaves when pushed beyond familiar limits. One reason this history is so satisfying is that it shows how small corrections can reshape large ideas. The black body problem was not about the origin of the universe, at least not on the surface. It was not about black holes, space-time foam, or maximum momentum. It was about radiation from warm objects, yet solving it required a change so deep that it eventually touched nearly every branch of physics. That is often how science works. The universe does not always reveal its foundations through dramatic phenomena. Sometimes it hides them in a curve on a graph, a mismatch in a calculation, a glow from an oven, or a stubborn detail that refuses to be ignored. Planck's own attitude toward his discovery adds a human softness to the story. He did not leap joyfully into quantum weirdness. He was in some ways pulled into it by necessity. The old theory failed. The data were clear. His mathematical solution worked. He accepted what he had to, even though the interpretation was uncomfortable. This is a valuable scientific virtue. It is easy to admire boldness, but there is also courage in reluctant honesty. Planck followed the problem where it led, even when it led away from the smooth classical world he valued. That willingness to be corrected by nature is one of the quiet strengths of science. The Planck constant also changed the meaning of measurement itself. In classical physics, one could imagine measuring a system as gently as desired, reducing disturbance without any fundamental limit. Quantum theory disturbed that dream. Measurements at small scales are interactions, and interactions come in quantum terms. You cannot simply look without participating. Light used to observe an electron can change the electron's motion. Pinning down one feature of a quantum system can make another feature less definite. The world is not merely hidden by poor instruments. It has a built-in structure that limits what can be jointly known and how sharply certain properties can be assigned. This is not a failure of human cleverness. It is part of the way the small world works. Momentum is deeply involved in that structure. The more precisely we try to localize something, the more momentum uncertainty enters the story. That fact becomes especially important as we approach tiny distances. To investigate smaller and smaller regions, we need probes with greater and greater momentum. But greater momentum means greater energy concentration. And if that concentration becomes extreme enough, gravity grows important. The quantum rules that began with Planck's radiation problem then lead us toward the gravitational edge of measurement. The same constant that saved the black body curve becomes part of the scale at which space-time itself may resist being divided further. Here the story begins to curve back toward our main subject. Planck momentum is not an isolated curiosity. It is a descendant of the quantum step. Without Planck's constant, there is no Planck scale in the same sense. Without the recognition that the microscopic world has discrete and uncertain features, momentum would remain a purely classical idea, useful but incomplete. With quantum theory, momentum becomes tied to wavelength, measurement, and uncertainty. With relativity, it becomes tied to energy and the cosmic speed limit. With gravity, it becomes tied to curvature. Put together, these ideas make Planck momentum feel less like a random maximum and more like a meeting place. It is where three great languages of physics begin speaking over one another, and we are still learning how to hear the combined sentence. There is also a practical contrast worth holding in mind. Planck's constant is tiny in everyday units, which is why quantum effects usually stay hidden from ordinary experience. But when it is combined with gravity and the speed of light, it helps produce Planck quantities that are extreme in different ways. Planck length is fantastically small, Planck time is fantastically brief, Planck energy is enormous by particle standards, Planck momentum is likewise far beyond anything we can directly produce for a single particle in present experiments. This contrast is part of the strangeness. A tiny constant opens the door to enormous limits. The small grain of quantum behavior leads, through gravity and relativity, to scales where our current theories reach their most severe test. The phrase, tiny doorway into enormous physics, is not just a pleasant image, it is almost literal in the intellectual sense. Planck found that energy exchange at microscopic scales required a tiny unit of action. That tiny unit became the doorway into atoms, photons, quantum fields, and the physics of the early universe. It also became part of the doorway into the Planck scale, where we ask whether space and time are continuous, whether momentum has a highest meaningful value, whether black holes store information in unexpected ways, and whether the universe at its deepest level is made of fields, strings, loops, networks, relationships, or something we have not yet named. A modest fix to a heat radiation problem became an entrance to questions so large that even our best theories stand at the threshold, peering in with cautious respect. As we move onward, it is useful not to imagine Planck momentum as something Planck himself fully developed in the modern sense. His name appears because his constant is one of the essential ingredients. The later meaning grew as physics expanded beyond his original problem. That is common in science. Names become attached to ideas that outgrow their first context. Newton did not know about galaxies in the modern sense, yet Newtonian gravity helped describe celestial motion. Maxwell did not build a smartphone, yet his electromagnetic theory helps make wireless communication possible. Planck did not set out to define a maximum momentum of nature, but his constant became part of the natural scale where such a question becomes unavoidable. This gives the subject a layered feeling. On one layer, there is the historical Max Planck, working in the world of heated cavities, radiation curves, and thermodynamic reasoning. On another, there is the quantum revolution that followed, transforming matter, light, and measurement. On a deeper layer, there is the Planck scale, where the constants of nature combine to indicate the frontier of quantum gravity. Planck momentum lives in that deeper layer, but its roots remain in the glow of hot matter and the refusal of classical physics to match what experiments showed. The grandest questions often keep such humble roots if we trace them carefully enough. For the mind settling down at night, this can be a pleasant way to hold the history. A glowing object troubled the old theory. A careful physicist introduced a tiny step. That step became a constant. The constant became a key. The key opened quantum mechanics. Quantum mechanics, joined with gravity and relativity, points toward Planck momentum. Nothing in that chain requires sudden drama. It unfolds through patient attention. A small mismatch becomes a new principle. A new principle becomes a new world. The universe, it turns out, can whisper through warm light before it roars through black holes. And now that the doorway is open, the next question is how the pieces actually fit together. Planck momentum is built from three deep ingredients: each carrying a different part of the story. One ingredient sets the quantum scale, the one Planck uncovered through the problem of radiation. Another sets the gravitational scale, telling us how energy and mass shape the geometry around them. Another sets the universal speed limit, binding space and time into a single relativistic structure. When these ingredients are brought together, not as a formal calculation here, but as a physical idea, they give us the natural momentum scale that bears Planck's name. To see why that combination matters, we need to look more closely at light, gravity, and quantum rules, and how they quietly conspire to define the edge where ordinary motion becomes something much stranger. To build Planck momentum in the mind without writing a single formula, it helps to imagine three very different messengers arriving at the same quiet table. The first messenger is light, the swiftest thing nature allows, carrying news about the speed limit of the universe. The second is gravity, patient and far-reaching, reminding everything that energy and mass are never completely separate from the shape of space and time. The third is the quantum rule that began with Max Planck, the rule that says the small world does not always behave like a smooth stream, but often comes in steps, limits, uncertainties, and packets of action. Each messenger tells a different story. Alone, each story is powerful. Together they begin to point toward a scale of momentum so extreme that ordinary physics starts to lose its comfortable furniture. Light is a good place to begin because light is the universe at its most disciplined. In empty space, light travels at the same speed for every observer, no matter how they're moving. That statement sounds simple until you realize it is the loose thread that pulled apart the old Newtonian picture of time and space. Before relativity, it seemed natural to think that speed should add in a straightforward way. If you run forward on a moving train, someone standing outside sees your running speed combined with the train speed. That feels sensible. It is the sort of thing a child can understand while running down a hallway, preferably not with scissors. But light refuses to behave like that. No matter how fast the source moves, no matter how fast the observer moves, light in empty space keeps the same speed. It does not politely add itself to your motion. It does not slow down because you are chasing it. It simply holds the line. That fixed speed is not just about light itself. It is the speed at which cause and effect can spread through the universe. It is the speed limit built into the structure of space-time. When we say nothing with ordinary mass can reach or exceed it, we are not merely stating a rule for fast objects. We are pointing to the way space and time fit together. As objects move faster and faster, their energy and momentum grow in ways that our everyday intuition cannot follow. A spacecraft can approach the speed of light, but every extra push gives less increase in speed and more increase in energy and momentum. The speed limit remains ahead, like a horizon that does not come closer no matter how determined the engine becomes. Physics is not being stubborn for fun. The geometry of reality is arranged so that this limit is preserved. Momentum, then, cannot be understood at extreme speeds, in the simple way we understand a thrown stone or a rolling cart. In daily life, faster motion usually means more momentum in a direct and familiar way. At very high speeds, close to the cosmic limit, momentum keeps growing even though speed has almost reached its ceiling. This is why light matters when we think about Planck momentum. The speed of light sets the relativistic part of the story. It tells us that there is a highest possible speed for signals and for massless things in empty space, and that momentum at extreme energies must be understood within that structure. Momentum is not just how far something goes. It is also how much energy and motion it carries in a universe where speed itself has a final boundary. The second messenger, gravity, seems at first like the opposite of light. Light is fast, sharp, and immediate. Gravity is quiet, persistent, and easy to underestimate. In ordinary life, gravity is familiar as weight, falling, and the reliable downward journey of anything knocked off a table by a cat with scientific curiosity. But in Einstein's theory, Gravity is not merely a force pulling objects together. It is the curvature of space-time caused by mass and energy. Matter and energy tell space-time how to bend, and that bending tells matter and light how to move. This is a very different picture from the old idea of invisible pulls acting across space. It makes gravity part of the stage itself. Most of the time, gravity is weak enough that we do not notice its deeper role. Between small particles, gravity is so faint compared with other forces that it might as well be whispering from another room. Electromagnetism dominates atoms and chemistry. The nuclear forces dominate the heart of atomic nuclei. Gravity governs planets, stars, galaxies, and the large-scale shape of the universe. But in the particle world it usually takes a back seat, possibly with a blanket and a quiet cup of tea. Yet gravity has one astonishing feature. It responds to energy, not just to mass sitting still, but to energy in all its forms. Motion, radiation, pressure, and momentum all contribute to the gravitational story. This matters because high momentum usually means high energy. If you concentrate enough energy into a small enough region, gravity stops being quiet. It stands up. It begins to curve space-time strongly. If the concentration becomes extreme enough, the region may form a black hole. That is not because the energy has turned into some special black hole substance. It is because space-time responds to concentrated energy by curving so intensely that a horizon can form, a boundary from which light cannot escape outward to distant observers. The lesson is simple but profound. Energy is not weightless in the deep sense. Momentum is not gravitationally irrelevant. Motion itself can help shape the arena in which motion occurs. Now bring in the third messenger, the quantum rule. This one is perhaps the strangest, because it speaks not with the grand sweep of light speed or the cosmic patience of gravity, but with the small-scale grammar of uncertainty. In quantum physics, particles are not just little pellets, with definite positions and velocities waiting for us to inspect them. Their behaviour is described by wave-like possibilities. Their momentum is connected to their wavelength. A particle with greater momentum corresponds to a shorter wavelength. A shorter wavelength allows us to probe smaller distances. That idea is central to modern particle physics. To look more deeply into matter, scientists use particles with higher and higher momentum because those particles can reveal structure on smaller and smaller scales. This is one reason particle accelerators are often described as microscopes, although they are microscopes in a very unusual sense. They do not use visible light and glass lenses to enlarge a tiny object for the eye. They use high-energy collisions to ask matter what it contains. When particles collide, the patterns of debris, the new particles created, and the directions and energies of everything flying outward tell scientists about the underlying rules. It is a little like learning about the inside of a watch by firing another watch at it and studying the pieces, which is not recommended for actual watch repair but has worked remarkably well for particle physics. Quantum rules also tell us that trying to confine something too tightly changes what can be said about its momentum. The more precisely we try to pin down where a particle is, the less settled its momentum becomes. This is not just a problem with clumsy instruments. It is built into the structure of quantum theory. Position and momentum are linked in a way that prevents both from being perfectly sharp at the same time. So when we ask what it would take to examine smaller and smaller distances, we are also asking about larger and larger momentum. The tiny world demands energetic questions. At first, this strategy seems endlessly promising. Use higher momentum, reach shorter wavelengths, examine smaller structures. This is how physics discovered layers within layers. Matter was not continuous stuff. It was made of atoms. Atoms had nuclei and electrons. Nuclei contained protons and neutrons. Protons and neutrons contained quarks and gluons. Each step required better tools, sharper probes, and greater energies. It is natural to wonder whether the process can continue forever. Could we simply keep increasing momentum and reveal smaller and smaller ingredients without limit? Planck momentum enters when the three messengers answer together. Light says that speed has a universal limit and that high momentum must be treated relativistically. Quantum theory says that higher momentum lets us probe shorter distances, but also brings uncertainty in wave behavior into the heart of the question. Gravity says that energy and momentum curve spacetime, and if concentrated too much, they may create horizons. Combine these lessons and an extraordinary possibility appears. To probe a distance as tiny as the Planck length, one would need momentum so enormous that the energy involved could no longer be treated as a harmless probe. Its gravity would matter. The probe might disturb spacetime so severely that the attempt to see the tiny distance would create a gravitational barrier. This is the conceptual birth of Planck momentum. It is the momentum scale that arises when the quantum need for short wavelengths meets the gravitational consequence of concentrated energy, all within the relativistic structure set by the speed of light. It is not built from human measurements. It is not based on the size of a laboratory, the strength of a machine, or the patience of a graduate student, heroic though that patience can be. It comes from the deep constants that appear to govern the physical universe. One constant sets the quantum scale, one sets the gravitational scale, one sets the light speed scale. Put them together in the right physical relationship, and the Planck scale emerges. Because we are avoiding formulas, it is helpful to describe the construction verbally. Start with the quantum rule that says smaller distances require larger momentum. Push the distance smaller and smaller, the required momentum rises. Now include gravity. Momentum carries energy, and energy gravitates. As the momentum rises, the gravitational effect of the probe grows. At ordinary scales, this effect is absurdly tiny. At very small scales, it becomes important because the energy is concentrated into a very small region. Keep pushing, and eventually the gravitational effect of the probing momentum becomes strong enough that the region you're trying to examine may be hidden behind a horizon, or altered beyond recognition. The scale where this conflict becomes unavoidable is the Planck scale. The corresponding momentum is Planck momentum. This picture does not require us to imagine a little speedometer on a particle with a red line labelled maximum. That would be too simple, and physics rarely leaves snacks that easy on the table. Planck momentum is better understood as a natural threshold of description. It marks the place where our familiar ideas of particle, wavelength, distance, energy, and space-time curvature all become entangled in one problem. Below that threshold, we can often keep quantum mechanics and gravity separate. We can study particles without worrying about their gravity. We can study planets and stars without worrying about quantum uncertainty in the shape of space-time. Near the Planck scale, that separation stops looking safe. There is a useful contrast here with the speed of light. The speed of light is a clear upper speed limit for objects with mass, and for the transmission of ordinary causal influence. Planck momentum is not established in exactly the same way as a universal maximum that every observer must agree upon under all circumstances. Momentum can depend on the observer's frame of reference in ordinary relativity. A particle that has moderate momentum for one observer may have much higher momentum for another moving differently. This is one of the reasons the phrase maximum momentum possible needs careful handling. In some speculative theories of quantum gravity, Planck momentum or Planck energy may become part of a deeper invariant limit. In ordinary established physics, it is safer to call it the natural momentum scale, where quantum gravitational effects are expected to dominate. That does not make it less important. In fact, it makes it more interesting. Physics is often most alive in the difference between what is known, what is suggested, and what remains unresolved. Planck momentum is not a confirmed object sitting neatly in a drawer. It is a signpost placed by the meeting of our best theories. It tells us that if we try to describe a single particle or interaction with momentum around that scale, we should not expect our usual tools to remain fully reliable. Quantum field theory on smooth space-time may be incomplete. General relativity without quantum uncertainty may be incomplete. The combination demands something deeper. One way to imagine the issue is to think about maps. If you are walking through a town, a street map is useful. It shows roads, parks, buildings, and bridges. If you zoom out to a country, you need a different map. If you zoom into the structure of a brick, the street map becomes useless. Not wrong exactly, just built for a different scale. Physics has maps too. Newtonian mechanics is an excellent map for many everyday motions. Relativity is a better map for high speeds and strong gravity. Quantum mechanics is the map for atoms and particles. Quantum field theory is a deeper map for particle interactions. But near Planck momentum, we reach terrain where the maps overlap badly. The paper tears a little. We can see that something is there, but the usual symbols no longer line up. The role of light in this map problem is especially important because light connects measurement to limits. To observe something, we usually need some kind of signal. Light is the most familiar signal, but particles can also be used as probes. The smaller the thing we want to resolve, the shorter the wavelength of the probing signal must be. Shorter wavelength means higher momentum. Higher momentum means more energy. More energy means more gravitational influence. So the act of seeing becomes part of the limit. Nature seems to prevent unlimited resolution not simply by hiding details, but by making the attempt to reveal them physically disruptive. The universe is not just a passive picture waiting for sharper focus. It responds to the focusing process. This response is mild in ordinary situations. Looking at a chair does not turn the chair into a black hole, which is considerate. Even powerful microscopes do not threaten spacetime. Our most energetic particle collisions are still far, far below the Planck scale for individual particles. The gap is enormous. It is not a matter of building a slightly larger machine next year, or asking the laboratory politely to plug in another extension lead. Planck momentum is so far beyond current experimental reach that direct tests are not available. This is why the subject belongs partly to theoretical physics, cosmology, black hole studies, and the search for quantum gravity. Still, the early universe may have come close to Planckian conditions. In the earliest moments we can imagine, temperatures and energies may have been so extreme that quantum gravity was important everywhere. The ordinary distinction between particles moving in spacetime and spacetime itself may not have existed in the familiar form. If Planck momentum has ever been physically relevant in a direct way, the very early universe is one of the places we would expect it. Black holes are another. Near singularities, if singularities are truly part of reality, and not signs that our equations have been pushed too far, densities and curvatures become extreme. Hawking radiation, black hole entropy, and information puzzles all suggest that quantum rules and gravity must eventually be combined. Planck momentum belongs naturally to that discussion. The construction from light, gravity, and quantum rules also gives us a more grounded way to understand the word maximum. In normal life, maximum means the largest allowed amount. The maximum speed on a road, the maximum number of biscuits one can eat before regret, the maximum volume before a neighbour begins communicating through the wall. In physics, maximum can mean several things. It can mean a strict proven limit. It can mean a practical limit set by available technology. It can mean a natural scale beyond which the old concept no longer applies. Planck momentum is most safely understood in the third sense, unless we are working within a specific theory that makes it stricter. It is the scale where asking for still more momentum within a tiny region may stop giving a clearer physical meaning and start demanding new structure. This is why Planck momentum does not simply say, here is the largest push. It says, here is where pushing becomes a question about space-time itself. A particle with ordinary momentum moves through space. A particle with high momentum can reveal smaller structure. A particle with Planck scale momentum may no longer be describable as a simple probe moving through a smooth arena. The arena may become quantum, curved, unstable, or horizon forming. At that point, the difference between the thing doing the probing and the space-time being probed begins to blur. There is a quiet elegance in how the ingredients balance. The quantum rule alone would encourage us to use ever higher momentum to examine ever smaller scales. Gravity alone would warn that concentrated energy curves space-time. Light alone would impose the relativistic structure that keeps speeds bounded and ties space to time. Together, they create a natural stopping point for old expectations. Not necessarily a final wall, but a boundary where the next theory must begin. That is why the Planck scale appears again and again in discussions of quantum gravity. It is the place where all three messengers can no longer be ignored. For a listener settling into the night, the most useful picture may be this. Imagine trying to knock on the smallest possible door in nature. Quantum physics says you need a very sharp knock, one with extremely high momentum to address something so tiny. Relativity says that this momentum carries enormous energy within the universal speed structure. Gravity says that if the knock is too concentrated, the door may not open at all. It may curve into a horizon. The knocking itself changes the doorway. Planck momentum is the scale of that strange knock, the point where asking a smaller question may create a larger problem. This does not mean the universe is refusing to be understood. It means understanding must change form. At every major boundary in physics, nature has seemed difficult before becoming clearer in a new language. The motion of planets looked mysterious before gravity. Light looked contradictory before electromagnetism and relativity. Atoms looked impossible before quantum mechanics. The Planck scale may be another such boundary. Planck momentum tells us where the language we already have begins to run out of breath. Beyond it may lie a theory in which space is not smooth, time is not fundamental, particles are not point-like, or momentum has a different meaning altogether. We do not know yet. But the signpost is there. The remarkable thing is that this signpost is built from such simple physical themes: motion, light, gravity, quantum uncertainty. None of these ideas is optional in modern physics. Momentum describes the persistence and direction of motion. Light sets the speed structure of the universe. Gravity makes energy and momentum part of the shape of space-time. Quantum theory limits how sharply small-scale properties can be defined and measured. When pushed together, they form Planck momentum, not as a decorative extreme, but as a warning that the deepest rules are meeting. So as the thought settles, we can hold the construction in words. To probe smaller distances, use higher momentum. Higher momentum means more energy. Concentrated energy curves space-time. At the smallest conceivable scale, where quantum behavior and gravitational curvature become equally unavoidable, the associated momentum is Planck momentum. It is the momentum of the boundary, the momentum of the unanswered question, the momentum scale at which the universe stops behaving like a quiet stage and begins behaving like a participant in the experiment. And once that is understood, the next difficulty becomes unavoidable, because calling it the maximum momentum possible sounds clear and satisfying, while the real physics behind that phrase is more subtle, more cautious, and more interesting than a simple upper limit. The phrase maximum momentum sounds wonderfully clear at first, almost comfortingly tidy. It seems to suggest a final value, the highest possible amount of motion that nature will allow before raising a hand and saying no farther. In everyday life, maximums are familiar. A lift has a maximum load. A kettle has a maximum fill line. A road has a maximum speed, although a surprising number of drivers appear to treat that as the beginning of a negotiation. So when we hear maximum momentum, it is natural to imagine the universe with a similar limit printed neatly on the side of reality. Up to here, motion is allowed. Beyond here, no entry. But Planck momentum does not behave quite like that simple picture. It is not a speed limit sign standing beside a cosmic motorway. It is not a proven barrier in the same clean way that the speed of light acts as a speed limit for objects with ordinary mass. It is better understood as a natural scale, a warning level, a point at which the physics we know begins to lose the ability to describe things in the usual way. That may sound like a small distinction, but it matters a great deal. A strict maximum says that nature forbids something. A natural scale says that our current concepts may stop being reliable there. One is a locked door, the other is a foggy border on a map, beyond which the landscape may continue, but our names for it may no longer fit. To see why this is subtle, we need to remember something important about momentum. Momentum depends on motion, and motion depends on the observer. A person sitting inside a train may place a cup on the table and see it resting quietly. Someone standing on the platform sees the cup rushing past with the train. The cup is not confused. The observers are simply using different frames of reference. In ordinary life, this difference is easy to manage. We say the cup is at rest relative to the train and moving relative to the platform. Both descriptions are valid. The same idea applies more deeply in relativity. Momentum is not a single universal fact that all observers must assign in the same way. It changes depending on how the observer is moving. This creates an immediate complication. If momentum can look different to different observers, what would it mean for there to be a maximum momentum? Suppose one observer sees a particle with a certain high momentum. Another observer moving very fast relative to the first may assign the particle a much larger momentum. In ordinary relativity, there is no simple universal cap on momentum, in the same way there is a universal cap on speed. The speed of light remains the same for all observers in empty space, and massive objects cannot reach it. Momentum, however, can keep increasing as an object is pushed closer and closer to that speed. The speed approaches a limit, but the energy and momentum can continue to grow without the same kind of ordinary ceiling in the established theory. This is why saying Planck momentum is the maximum possible momentum needs careful handling. In some approaches to quantum gravity, physicists explore the idea that Planck scale quantities might become true limits in a new and deeper theory. There are speculative frameworks where the Planck energy, Planck length, or Planck momentum may be observer independent in some modified sense. These ideas are serious enough to be studied, but they are not settled facts. We do not yet have experimental proof that momentum is capped at the Planck value for every observer and every physical situation. What we do have is a powerful clue. When momentum reaches the Planck scale in a localized process, the usual separation between quantum physics and gravity is expected to fail. That word localized is doing important work. A large object can have enormous total momentum simply because it is massive and moving. A planet orbiting a star carries a vast amount of momentum by ordinary standards. A galaxy drifting through space carries more still. But that is not what physicists usually mean when they discuss Planck momentum as an extreme quantum gravity scale. The issue is not just total momentum spread over a huge object. The issue is momentum concentrated into a very small region, or associated with a single particle like probe trying to explore tiny distances. A cargo ship can carry a huge amount of momentum, but its energy is spread over a large structure. It does not tear open the quantum fabric of space-time with every trip across the ocean. It mostly causes paperwork and waves. Planck momentum becomes meaningful when we think about extremely small distances. In quantum physics, a higher momentum means shorter wavelength, and shorter wavelength means a sharper probe. If you want to examine a smaller region, you need a probe with greater momentum. But once that momentum becomes fantastically high and is concentrated into a tiny space, gravity can no longer be ignored. The energy tied to that momentum curves space-time. If the concentration is extreme enough, the attempt to probe smaller distances may create a horizon, the defining boundary of a black hole. In that case, higher momentum would not give better vision. It would hide the region behind gravitational darkness. More force would not sharpen the microscope. It would break the idea of a microscope. This is a key reason Planck momentum is often treated as an upper meaningful scale, rather than simply a largest number. The difficulty is operational. Physics is not only about what numbers can be written down, it is about what can be measured, prepared, observed, and given physical meaning. If trying to create or measure a momentum beyond a certain scale causes the measurement process itself to collapse into a black hole, then the idea of accessing smaller distances through greater momentum becomes self-defeating. Nature may not need to forbid the number in a simple way. It may simply make the procedure for giving that number meaning impossible within the old framework. There is an old habit in physics of thinking that more energy means deeper access. This habit has been incredibly successful. To understand atoms, scientists used probes energetic enough to disturb them. To understand nuclei, they used still more energetic probes. To understand the inner structure of protons and neutrons, they used high-energy collisions. The pattern seems clear. If matter has smaller pieces, hit harder and look at what comes out. This method has revealed a breathtaking amount. It has taken us from chemistry to nuclear physics to quarks and gluons, from visible matter to quantum fields. But the Planck scale suggests that this strategy may have a final change of character. At some point, hitting harder may not reveal smaller ingredients. It may create a gravitational object whose horizon prevents the desired information from escaping. That possibility changes the meaning of maximum. Instead of imagining a wall in momentum space, imagine a method that stops working. A fisherman may cast a net into a pond and catch fish. A larger net may catch more, but if the net becomes so large and heavy that it sinks the boat, the problem is no longer fishing technique. The tool has become part of the crisis. In the same way, momentum is a tool for probing small distances. Planck momentum marks the scale where the tool becomes gravitationally dangerous. The question shifts from what smaller thing can we see to whether seeing smaller things in the usual way still makes sense. There is another subtlety. Momentum in curved space-time is not always as globally simple as it is in ordinary flat space. In flat space, with no gravity or with gravity ignored, conservation of total momentum can be defined cleanly. The background is stable and uniform. In general relativity, space-time itself can curve, stretch, expand, and carry gravitational waves. In some situations, defining total momentum for the entire universe is tricky. Local momentum still makes sense. A particle passing through a small region can have momentum as measured by a nearby observer. But the global bookkeeping becomes more delicate when the stage itself is dynamic. This is not a flaw in the theory. It is part of the price of making space-time an active participant rather than a fixed background. This matters because Planck momentum belongs to a region where space-time may be not only curved but quantum uncertain. If ordinary curved space-time already makes global momentum more subtle, then a quantum version of space-time may make the idea even more complex. We're used to picturing momentum as something an object carries through a pre-existing arena. Near the Planck scale, the arena may not be pre-existing in the familiar sense. It may fluctuate. It may have discrete features. It may be emergent from deeper relationships. Different theories suggest different possibilities. If space itself is not smooth at the smallest scale, momentum may not be defined there in the same way it is in a laboratory beamline. This is one reason the phrase maximum momentum possible can be misleading if heard too literally. Possible in which theory? Possible for which observer? Possible for a single particle, a field mode, a localized collision, a whole galaxy, or a universe? Possible as a value in an equation, or possible as something physically measurable? A phrase that sounds simple begins to branch into many careful questions. Physics often works like this. A childlike question opens the door. Then the grown-up details arrive carrying notebooks. Still, we should not make the idea seem weaker than it is. Planck momentum is not just a vague guess. It is a natural and deeply motivated scale. When the constants of quantum physics, gravity and relativity are combined, the Planck scale appears. This is not a matter of taste. It is a sign that our existing theories contain within themselves a pointer to their own boundary. They are, in effect, telling us where they expect trouble. That is remarkably useful. Even without a completed theory of quantum gravity, the Planck scale gives physicists a way to estimate where new physics should appear. It tells us that any attempt to describe interactions at such extreme momentum and tiny distance must treat quantum effects and gravitational effects together. There are several ways physicists think about what may happen there. One possibility is that Planck momentum represents a real maximum in a future theory. Momentum may be modified so that it cannot exceed a certain value, much as speed cannot exceed the speed of light for massive objects. Another possibility is that momentum can still be mathematically larger in some descriptions, but attempts to localize it create black holes or other gravitational states, preventing access to sub-Planckian distances. Another possibility is that the very concepts of distance and momentum are emergent, so asking what happens beyond the Planck scale is like asking what lies north of the North Pole. The question may not be wrong emotionally, but the coordinates have stopped applying. That last comparison is useful because it shows how limits can be conceptual rather than mechanical. The North Pole is not surrounded by a wall. You can stand there, turn around, and walk away. But once you're at the North Pole, every direction along the surface is south. The word north no longer points to a further place. In a similar spirit, the Planck scale might mark a place where smaller distance or greater localized momentum no longer means what it used to mean. It is not that a tiny guard appears and confiscates your particles, it is that the language of the question changes under pressure. The history of physics contains many such shifts. Before relativity, time seemed absolute. Then Einstein showed that time depends on motion and gravity. The old question of what time is everywhere at once had to be revised. Before quantum mechanics, particles seemed as though they should always have definite positions and speeds. Then quantum theory showed that nature does not permit all classical properties to be sharp together. The old question of where exactly is the particle and how fast exactly is it moving had to be revised. Planck momentum may be pointing toward another revision. The old question of how much momentum can we give a particle to probe a smaller distance may need to become a question about what distance, particle, and momentum mean when spacetime itself is no longer smooth and classical. There is also a difference between a technological maximum and a physical maximum. Our present particle accelerators are limited by engineering, funding, materials, magnets, power, and the inconvenient fact that the Earth is only so large. These are practical limits. They may change over time. Future civilizations might build larger accelerators, use astrophysical processes, or find methods we have not imagined. But Planck momentum is not merely a current engineering challenge. It is so far beyond present particle energies that reaching it by conventional acceleration would require conditions unlike anything we can build. More importantly, it may not be reachable as an ordinary beam particle in a meaningful way, because the gravitational consequences would become central. So when we say maximum, we are not saying our machines are not strong enough yet. We are saying the nature of measurement itself may change. Natural cosmic accelerators can produce particles with energies far beyond our laboratories. Cosmic rays strike Earth from space with astonishing energy. Some are far more energetic than particles in human-made accelerators, yet even these are still enormously below the Planck scale. This gap reminds us how extreme Planck momentum really is. It is not merely the next hill after the one we have climbed, it is another continent, perhaps another planet, perhaps a place where the idea of roads has become suspicious. That distance from experiment is one reason caution is essential. We can reason toward the Planck scale, but we cannot yet test it directly in the simple way we test lower energy particle physics. There may, however, be indirect clues. Some theories suggest that Planck scale physics could leave faint traces in the behavior of light traveling across the cosmos, in the early universe, in black hole evaporation, or in tiny violations or modifications of familiar symmetries. Scientists look for such effects carefully. So far, no confirmed signal has forced a single answer. That absence is important. It means that Planck momentum remains a guide, not a fully explored territory. It is a place where theory must be imaginative but disciplined. Too much imagination without discipline becomes fantasy. Too much discipline without imagination never leaves the porch. Physics needs both, preferably with good coffee. The observer dependence of momentum remains one of the most important conceptual thorns. In ordinary relativity, you can always choose a frame moving relative to a particle so that its momentum looks different. If there were a universal maximum momentum, the transformation between observers would need to be modified or reinterpreted. Some theoretical ideas attempt exactly that. They propose that the Planck scale might be invariant, meaning all observers agree on it in some deep way, just as all observers agree on the speed of light. This is an appealing possibility because it would make the phrase maximum momentum more literal. But modifying relativity is delicate. Relativity is tested extremely well. Any change must preserve its successes while explaining why deviations only appear near the Planck scale. That is a demanding requirement. Another way to approach the issue is to focus not on the momentum assigned by arbitrary distant observers, but on what a local physical process can concentrate and measure. A distant observer may describe a particle with very high momentum because of relative motion, but the local conditions in the particle's own interaction frame may be different. Black hole formation, scattering, and quantum gravity effects depend on invariant features of the interaction, such as how much energy is available in the center of the collision and how tightly it is concentrated. This is why careful physicists often avoid loose statements about a single particle simply having maximum momentum in all contexts. The meaningful question is what happens in a physical interaction when Planck scale momentum transfer is involved. Momentum transfer is an especially useful phrase here. In experiments, what reveals structure is not just that a particle has momentum, but that momentum is exchanged during an interaction. A probe scatters, changes direction, creates new particles, or leaves a measurable trace. The sharper the probe, the larger the momentum transfer involved. Planck scale momentum transfer would mean trying to resolve distances so tiny that gravitational collapse or quantum spacetime effects may intervene. So the maximum may not be about a particle cruising peacefully through the universe with a forbidden amount of motion. It may be about the greatest meaningful sharpness of a probe before the idea of probing breaks down. This leads to a very different emotional picture. Instead of the universe as a strict traffic officer, imagine it as an ocean. At low waves, you can measure ripples clearly. At larger waves, you can still track crests and troughs. But if you try to create a wave so sharp and intense that it changes the water surface violently, breaks, foams, and pulls in the measuring device, the original idea of measuring a neat ripple no longer applies. Planck momentum is like the scale where the wave you use to measure the ocean may become a storm in the ocean itself. The limit is not just imposed from outside, it arises from the interaction between the probe and the medium. The difficulty is that space-time may not be a medium in the ordinary sense either. General relativity treats it as geometry. Quantum gravity may treat it as something deeper or emergent. Some approaches suggest that areas or volumes come in discrete units. Others suggest that strings rather than point particles smooth out the violent short-distance behavior. Others build space-time from networks of relationships, causal structures, or quantum information. In each case, Planck momentum may play a different role. It may be a maximum, a transition, a conversion scale, or a sign that different variables should replace momentum at the deepest level. The shared message is that ordinary high momentum thinking cannot continue unchanged. This is why the topic is so rich. A simple phrase like maximum momentum possible turns into a lesson in humility. It forces us to ask what a physical quantity means, how it is measured, who is measuring it, what theory defines it, and whether the underlying stage is stable enough for the question. Momentum began as the stubbornness of moving objects. It became a conserved quantity tied to the symmetry of space. It became part of relativity, linked with energy. It became quantum, tied to wavelength and uncertainty. Then, at the Planck scale, it becomes gravitational, pulling the structure of spacetime into the discussion. By the time we reach maximum momentum, we're no longer talking only about motion. We're talking about the conditions under which motion remains a meaningful concept. For all that subtlety, the basic intuition remains valuable. Planck momentum marks the point where a localized momentum becomes so extreme that trying to use it as a sharper probe likely fails within known physics. The probe may form a black hole. The spacetime around it may fluctuate quantum mechanically. The separation between object and geometry may dissolve. A future theory may turn this into a strict maximum, or it may reveal a deeper structure in which the question is transformed. Either way, Planck momentum is not just a large amount of motion, it is a boundary in understanding. So when we use the phrase maximum momentum possible, we should hear it in a careful scientific way. It does not mean we have directly watched nature reject a particle for carrying too much momentum. It does not mean every kind of total momentum in the universe is capped in the same simple fashion. It means that the Planck momentum is the natural scale at which our usual description of localized momentum, distance, energy, and space-time can no longer be trusted without quantum gravity. It is the scale where the universe seems to stop answering the old question and begins preparing a harder one. That harder question leads naturally toward the most extreme objects we know how to discuss with some confidence. If concentrated energy and momentum can curve spacetime strongly enough to create horizons, then black holes are not a side topic. They are central to the story. Particles with greater and greater momentum, collisions with greater and greater concentration, and the gravitational collapse that may follow are all part of the same path. To understand why pushing harder eventually gets strange, we have to bring particles and black holes into the same room. Even if one is tiny, the other is cosmic, and both have a habit of making physicists stare quietly at the ceiling for a while. When particles and black holes are brought into the same discussion, it can feel at first like we have placed a grain of dust beside a mountain and asked them to compare notes. A particle is the smallest sort of thing we usually talk about in physics, or at least one of the smallest useful things. A black hole is among the most extreme large-scale objects in the universe, a region where gravity has become so intense that light itself cannot escape once it crosses the boundary. One belongs to the language of quantum theory, accelerators, detectors, probability, and tiny flashes of energy. The other belongs to the language of collapsed stars, curved space-time, event horizons, and the strange darkness left behind when gravity wins completely. They seem like opposites. Yet when momentum is pushed high enough and concentrated tightly enough, these two worlds begin to lean toward each other. That is one of the most important lessons hidden behind Planck momentum. Extreme momentum is not merely a matter of making a particle go faster, as if the universe were a long empty road and the particle were an unusually determined motorcycle. At ordinary energies, that picture is already too simple, but it still works well enough as a rough guide. At very high energies, the guide begins to fail. A particle with enormous momentum also carries enormous energy. If that energy is squeezed into a tiny enough region, gravity notices. At first it notices faintly, like someone half awake hearing a floorboard creak downstairs. Then, at the Planck scale, gravity is no longer half awake. It is sitting upright, turning on the lamp, and asking what exactly is going on. In particle physics, pushing harder has a clear purpose. Scientists accelerate particles to higher and higher energies because high momentum particles can probe smaller and smaller structures. This is one of the great practical ideas in modern physics. Visible light cannot reveal the interior of an atom because its wavelength is too large compared with the structures we want to see. To investigate smaller distances, we need shorter wavelengths. In quantum physics, shorter wavelength is linked to greater momentum. So a high momentum particle becomes a sharper probe. It can scatter from tiny structures and reveal details that lower momentum probes would simply wash over. This approach has worked beautifully. It helped uncover the atomic nucleus. It helped reveal that protons and neutrons are not simple solid beads, but are made of quarks bound by gluons. It helped establish the modern picture of particle physics, where matter and forces are described by quantum fields and their excitations. Each increase in energy allowed scientists to ask nature a more precise question. What happens inside this smaller region? What hidden pattern appears when matter is struck more sharply? What new particles can be created when enough energy is gathered into a collision? There is something almost old-fashioned about the method, even though the machines are incredibly advanced. It has the spirit of testing a locked object by tapping, shaking, and eventually opening it with better tools. The difference is that in particle physics, the tool is not a screwdriver. It is a beam of particles moving with extraordinary momentum. When those particles collide, the collision region briefly becomes a place where energy is concentrated into a tiny volume. New particles can appear from that energy, because in modern physics, energy and matter are deeply interchangeable. The detector surrounding the collision reads the aftermath, tracks the paths, measures the deposits, and reconstructs what happened in the tiny central flash. For a long time, one might imagine this method could continue without any deep change. Build a larger accelerator, use stronger magnets, reach higher energies, ask sharper questions, look at smaller scales, repeat until reality finally admits what it is made of. This is a tempting dream, and in many ways it has been the dream of high-energy physics. But gravity adds a complication that cannot be ignored forever. Energy curves space-time. If enough energy is concentrated into a small enough region, the region can become hidden behind an event horizon. That is the basic idea of black hole formation. A black hole is not made only by a dying star. In principle, any form of energy compressed tightly enough can create the same kind of gravitational trap. This is where pushing harder gets strange. A particle collision at ordinary or even very high laboratory energies is not close to forming a black hole. The gravitational effect of the particles is fantastically weak. Other forces dominate completely, but as we imagine higher and higher momentum concentrated into smaller and smaller distances, the gravitational field associated with that energy grows more important. Eventually, the same momentum that should have sharpened the probe may make the probe collapse into something that hides information rather than reveals it. The collision no longer acts like a microscope. It acts more like a tiny furnace of gravity, possibly forming a microscopic black hole if the conditions are extreme enough. This does not mean black holes are expected to appear in our current accelerators under ordinary physics. The energies involved are far too small compared with the Planck scale. There have been speculative ideas in certain models with extra dimensions where microscopic black holes could appear at lower energies, but ordinary expectations place true Planck scale gravity far beyond our machines. The important point for our discussion is conceptual. In the usual path of discovery, higher momentum means finer resolution. Near the Planck scale, higher momentum may no longer mean that. It may mean that the attempt to concentrate energy enough to see a smaller distance produces a gravitational horizon. More effort gives less access. A horizon changes everything. Outside a black hole, information about what crosses the horizon cannot simply travel back out in the usual way. Light cannot escape outward once it is inside. For an outside observer, the horizon marks a limit on what can be directly observed. If a high momentum collision creates a tiny horizon, then the details of the collision at even smaller distances may be hidden. Instead of seeing the inner structure you hope to reveal, you see the signs of a gravitational object forming and perhaps later evaporating. Nature does not hand over a sharper image, it gives you a boundary. This is one of the deepest reasons physicists suspect there may be a minimum meaningful length or a maximum meaningful localized momentum. The issue is not that our instruments are too crude. It is that the act of using more momentum to resolve smaller scales changes the gravitational situation. In ordinary microscopy, brighter light can improve visibility up to a point, although too much light may damage a delicate sample. Near the Planck scale, this idea becomes extreme. The sample is space-time itself, and the light or particle used to probe it may carry enough energy to distort or conceal the very region under investigation. The microscope becomes part of the geometry. Black holes are useful in this story because they teach us that size and energy are linked in an unexpected way. For ordinary objects, adding energy or mass often makes the object larger or more complicated. A larger planet has more material spread across a larger volume. A hotter gas expands if it can. But a black hole is different. The more mass or energy a black hole has, the larger its horizon. This means that if a collision energy becomes great enough to make a black hole, adding still more energy does not let us probe smaller distances. It makes the horizon larger. That is the opposite of the usual particle physics strategy. The harder you push, the bigger the region hidden from view may become. This reversal is central. At low and moderate energies, more momentum means shorter wavelength and better resolution. At Planck scale energies, gravity may reverse the trend. More concentrated energy may create a larger gravitational radius. The universe seems to say that beyond a certain point, the route to smaller distances is blocked not by weakness, but by strength. The probe is too powerful. It bends the arena too much. It becomes the thing you must study instead of the thing that helps you study. There is an almost practical lesson here. Though the setting is unimaginably extreme, a tool is useful only while it does not destroy the conditions that make the task meaningful. A thermometer is useful for measuring the temperature of a cup of tea because it does not greatly change the tea. A heavy brick dropped into the cup also interacts with the tea, but it is not a better thermometer. It changes the situation too violently. At ordinary quantum scales, a high momentum particle is like a delicate but sharp probe. Near the Planck scale, it begins to resemble the brick, not because it is large, but because its concentrated energy has gravitational consequences that cannot be ignored. This is also why point particles become suspicious near the Planck scale. In many successful theories, particles are treated as point-like, meaning they have no measurable internal size at the scales we can test. This description works extremely well in quantum field theory. But if you try to push a point-like object to arbitrarily high momentum, you run into the issue of concentrating energy into arbitrarily small regions. Gravity does not allow us to ignore that forever. A point with limitless energy concentration is not a harmless mathematical convenience once gravity is present. It is a warning sign. It may indicate that the theory needs a new description before such extremes are reached. Different approaches to quantum gravity respond to this warning in different ways. In string theory, the basic objects are not point particles but tiny extended strings. At ordinary scales, they may behave like particles, but at extremely small scales, their extended nature can soften some of the violent behavior that point particles create. In loop quantum gravity, geometry itself may have discrete features, with areas and volumes not divisible without limit in the usual sense. In other approaches, spacetime may emerge from quantum information, causal relationships, or deeper structures that do not resemble ordinary space at all. These theories differ, but they share the sense that the Planck scale is not simply more of the same. It is where the old picture needs help. Black holes also bring in another clue, one that seems at first unrelated to momentum, but is deeply connected to the question of limits. Black holes have entropy. Entropy is often described as a measure of how many microscopic arrangements correspond to the same overall state. For black holes, the entropy is linked not to the volume inside, but to the area of the horizon. That is a strange and important result. It suggests that the amount of information that can be stored in a region may be limited by the boundary around it, not by the volume in the ordinary way. This idea has led to the holographic principle, the possibility that the information content of a region of space might be described by degrees of freedom on its boundary. If that sounds unusual, it should. It is one of the clearest signs that gravity, quantum theory, and information are deeply entangled. It also supports the idea that there are limits to how much physical detail can be packed into a region. If information storage itself has gravitational limits, Their momentum used to probe tiny distances is part of a broader story. The universe may not allow unlimited independent detail inside a fixed region, at least not in the way ordinary field theory might suggest without gravity. Black holes become not only objects of destruction, but teachers of counting. They tell us that space, energy, and information obey rules we do not yet fully understand. This returns us to Planck momentum. A particle with Planck scale momentum, localized to a Planck scale distance, would be associated with the threshold where quantum wavelength and gravitational horizon become comparable in meaning. The particle is no longer just a quantum object moving through a background. It is also a gravitational object, or at least something whose energy is strong enough to challenge the background description. Try to localize it more tightly, and quantum uncertainty pushes momentum higher. Push momentum higher, and gravity curves space-time more strongly. The two tendencies squeeze the old picture from both sides. It is important to say this carefully. Planck momentum is not the momentum of a normal black hole in the sky. Stellar black holes have masses and total momenta vastly different from this scale. A black hole drifting through space can have a large momentum depending on its mass and motion relative to an observer. The Planck momentum is not about every black hole as a whole. It is about the natural scale for a localized quantum gravitational process. It is the kind of momentum that appears when the wavelength associated with a quantum object becomes comparable to the scale at which its own gravity can no longer be neglected. At that threshold, the line between particle and black hole may blur. A particle is usually described by quantum fields, with interactions taking place in spacetime. A black hole is described by geometry, horizon, mass, charge, spin, and thermodynamic properties. Near the Planck scale, an object might not be cleanly one or the other. It might be a quantum gravitational state, with particle-like and black hole-like aspects. We do not know exactly how to describe such a thing because we do not yet have a completed, experimentally confirmed theory of quantum gravity. But the expectation that something changes is not arbitrary. It follows from bringing together the rules we already trust in their own domains. The phrase pushing harder gets strange also applies to force itself, although momentum is our main focus. In ordinary mechanics, applying a force changes momentum. Push a cart and its momentum changes. In particle accelerators, electric fields increase particle energy and momentum, while magnetic fields steer the beam. But as speeds approach the speed of light, pushing a massive particle does not make it exceed that speed. Instead, the particle's energy and momentum continue increasing. This is already one kind of strangeness. Relativity teaches that speed is not the only measure of motion. Momentum can grow enormously, while speed barely changes. Then gravity adds the deeper strangeness. If the momentum and energy become concentrated enough, pushing harder does not simply make a sharper particle. It risks changing the geometry around the particle. This is where the everyday idea of effort becomes misleading. We're used to thinking that more effort produces more of the intended result. More push, more speed, more magnification, more detail, more energy, deeper access. But nature often has regimes where an input changes the rules of the game. Heat water and it gets hotter until it boils. Compress a gas and its pressure rises until new physical effects appear. Push matter to nuclear densities and atoms are no longer the right building blocks. Push momentum to the Planck scale and space-time may no longer be the quiet background. There is also a connection to scattering, one of the most important tools in physics. Scattering means sending something towards something else and watching how it comes away. Rutherford used scattering to reveal the atomic nucleus. Modern colliders use scattering to reveal particle interactions. The sharper the scattering, the larger the momentum transfer, and the smaller the distance being tested. But gravitational scattering at extremely high energies may become dominated by black hole formation. Instead of two particles exchanging a force carrier and flying away with clear information about tiny distances, they may form a trapped region. The outgoing information, if any, may be thermal, scrambled, or encoded in subtle correlations through processes like black hole evaporation. The clean scattering experiment becomes a problem of quantum gravity and information. This is why black holes are not merely obstacles in this story. They may be the form that extreme collisions naturally take. If so, then the Planck scale is less like a wall and more like a change in species. Below it, high momentum particles probe structure. Around it, high momentum concentration creates gravitational states. Above it, if that phrase even remains meaningful, the relevant objects may be larger black holes rather than smaller distances. The direction of discovery turns around. More energy makes larger horizons, not finer images. A helpful image is to imagine trying to read smaller and smaller print with stronger and stronger lenses. For a while, stronger lenses help. Then imagine that beyond a certain strength, the lens becomes so massive that it bends the page, then traps the light from the page, then becomes the object you're forced to study. You have not failed because you lacked ambition. You have reached a regime where the method changes the target. The Planck momentum is the scale where the lens, the page, and the act of reading all become part of one gravitational quantum problem. This does not make the Planck scale hopeless. It makes it fascinating. Black holes may actually provide clues about the theory we need. Hawking's discovery that black holes can radiate gave physicists a rare bridge between quantum theory, gravity, and thermodynamics. The black hole information problem asks whether information that falls into a black hole is lost or somehow preserved in the radiation and correlations. Most physicists now suspect that information is preserved, though the exact mechanism has been debated for decades. This suggests that quantum gravity must encode information in a way unlike ordinary local field theory. The same deep rules that resolve black hole evaporation may also explain what Planck momentum truly means. There is a practical humility here. We cannot build a Planck momentum particle beam and watch a tiny black hole form under controlled conditions. The energies are far beyond current technology, and the theoretical interpretation would be difficult even if we could. Instead, physicists use consistency. They ask how quantum theory, relativity, thermodynamics, and information can fit together without contradiction. Black holes are where contradictions become sharpest. They are nature's stress test for our ideas. If a proposed theory handles black holes, horizons, entropy, and quantum information well, it may be pointing in the right direction. If it fails there, it probably cannot explain Planck momentum either. For our purposes, the central point is calm but powerful. Particles teach us how to use momentum to ask smaller questions. Black holes teach us that concentrated energy can hide answers behind horizons. Planck momentum lies where these teachings meet. It is the scale where a particle used as a probe may become gravitationally significant, where shorter wavelength no longer guarantees smaller resolution, and where pushing harder may create a larger boundary instead of a clearer view. That is why the maximum momentum possible is not simply the biggest shove nature allows. It is the point where the act of shoving changes what space, time, and measurement mean. The ordinary world continues peacefully far below this threshold. A rolling ball remains a rolling ball. A train remains a train. A beam of light from your bedside lamp does not threaten the geometry of the room. Even the most energetic events we routinely handle in technology are gentle compared with the Planck scale. But physics often learns by following ordinary ideas until they become extraordinary. Momentum begins as the stubbornness of motion. In accelerators, it becomes a tool for discovery. Near black holes, it becomes part of gravity's source. At the Planck scale, it becomes a question about whether the familiar stage of space and time can survive being examined too closely. So the story moves from particles flying through detectors to horizons forming in theory, from sharper probes to hidden regions, from pushing harder to discovering that harder is not always clearer. The next step is to look directly at the Planck scale itself, not just as a collection of extreme values, but as the region where space, time, and motion may lose the meanings they carry so comfortably in ordinary life. At the scales we are used to, space feels like a roomy, reliable place. It is left and right, up and down, near and far. You can walk across a room, place a book on a table, measure the length of a wall, or lose your keys somewhere that definitely has a location, even if that location seems to be known only to the keys. Space feels continuous. If 2 points are separated by a meter, we can imagine halfway between them, then halfway again after that. Our minds are comfortable with the idea that distance can be divided without limit, at least in thought. Time feels much the same. An hour can be split into minutes, minutes into seconds, seconds into smaller intervals, and the mind assumes that the cutting can continue forever, if only our clocks are delicate enough. The Planck scale challenges that comfortable assumption. It does not necessarily tell us that space and time are definitely made of tiny pieces in the same way a beach is made of grains of sand. That would be too simple, and perhaps too satisfying. Instead, it tells us that when we try to discuss distances as small as the Planck length, times as brief as the Planck time, and momenta as extreme as Planck momentum, the usual meanings of distance, duration and motion may no longer apply in the way we expect. Our familiar concepts are not exactly proven false there. They become uncertain tools. Like using a map of country roads to navigate the inside of an atom, the old language may still have a history, but it no longer has enough detail to guide us. This is one of the strangest lessons in modern physics. Space and time may not be endlessly smooth backgrounds waiting for smaller and smaller rulers. They may have a limit to how finely they can be examined, or they may emerge from something deeper that is not space or time in the ordinary sense. At the Planck scale, we do not simply face a technical problem of building better instruments. We face a conceptual problem. What would it mean to measure a distance so small that the energy needed to perform the measurement could curve space-time violently? What would it mean to speak of a time interval so brief that before and after may not be sharply defined? What would motion mean if the stage on which motion happens is itself fluctuating, uncertain, or not yet fully formed? To see why the Planck scale is so disruptive, it helps to begin with an everyday picture of smoothness. Imagine a calm pond on a still morning. From a distance, the surface looks continuous and glassy. A leaf floating across it traces a clear path. A ripple spreads outward smoothly. You could describe positions and motions using ordinary geometry, and nothing would seem strange. Now imagine leaning closer. At some point you remember that water is made of molecules. The smooth surface is not smooth in the deepest sense. It is an average behaviour of many tiny parts. The pond has not become unreal. The smoothness was real at the scale where you first observed it, but it was not fundamental all the way down. Some physicists wonder whether space-time may be similar. At human scales, and even at atomic and nuclear scales, space-time behaves as if it is smooth. General relativity treats it as a flexible geometry, able to curve around mass and energy. That theory has been tested with extraordinary success. It explains planetary motion, gravitational lensing, black holes, gravitational waves, and the corrections needed for satellite navigation. For almost every large-scale purpose, space-time as a smooth fabric works beautifully. But the Planck scale asks whether that smooth fabric remains meaningful at the smallest possible distances. Perhaps it does, perhaps it does not. We do not yet know. But our best clues suggest that something unusual must happen. The reason is the meeting of two pressures. Quantum physics tells us that the smaller a region we try to examine, the more momentum and energy our probe must carry. Gravity tells us that energy curves space-time. So if we try to examine a region as tiny as the Planck length, the probe required is not gentle. It is not a little candle held up to a small object. It is more like trying to inspect the dust on a window by firing a lightning bolt at it. The probe has so much energy packed into such a small region that the geometry around it may be strongly affected. The act of measurement no longer simply reveals space-time. It may disturb it so much that the old idea of a measured point loses meaning. This is why the Planck length is often described as the smallest meaningful length, though that phrase also needs care. It does not mean physicists have placed a tiny ruler on the table and found the final notch. It means that below this scale, our known theories no longer let us speak confidently about distance in the usual way. If we try to define a smaller distance using higher momentum, gravitational effects may prevent the measurement from giving a clearer result. The attempt to sharpen the picture may create a horizon or a quantum gravitational disturbance. The concept of a point in space, so natural in mathematics, may not correspond to something physically measurable without limit. This can feel unsettling because points are everywhere in our thinking. We imagine an object being here rather than there. We imagine a particle following a path. We imagine a ruler laid across space and a clock ticking through time. But physics has already taught us that everyday imagination is not always the final judge. An electron does not move like a tiny planet around a nucleus, even though that picture is easy to draw. Time does not pass at the same rate for everyone, even though that feels obvious. Light is both wave-like and particle-like, in ways that resist simple images. So it should not surprise us too much that space itself may stop behaving like an infinitely divisible container at the deepest scale. The Planck time adds another layer. It is the time associated with light crossing a Planck length. In ordinary speech, that is almost impossibly brief. It is so brief that our minds cannot really picture it. We can name it, but we cannot feel it. Human experience is built from heartbeats, breaths, footsteps, days, and seasons. Even the fastest events in ordinary technology are slow compared with the Planck time. At that level, asking what happened before or after may become difficult, not because there is no sequence anywhere, but because the classical idea of a smooth time coordinate may not survive. Time may be part of the same quantum gravitational uncertainty as space. This is a major challenge because quantum theory and general relativity treat time differently. In ordinary quantum mechanics, time often appears as a background parameter, something external that tracks how a system changes. In general relativity, time is not external. It is part of space-time shaped by gravity and motion. Near the Planck scale, both descriptions are needed, but they do not fit together cleanly. If space-time itself is quantum, then time cannot simply be an untouched clock outside the system. But if time is not an ordinary background, then the usual quantum description becomes harder to interpret. The result is known as the problem of time in quantum gravity, and it remains one of the deep unresolved puzzles in theoretical physics. Motion depends on both space and time. To say something moves means that its position changes with time. If space and time lose their usual meanings near the Planck scale, motion must be reconsidered as well. A particle moving through a smooth background is a familiar idea. A wave spreading through a field is also familiar to physicists. But if the background is fluctuating or emergent, if the geometry itself has quantum uncertainty, then motion may not be a simple path through a pre-existing arena. The path may be only an approximate concept that appears at larger scales, like the smooth surface of a pond appearing from many molecules. This has direct relevance to Planck momentum. Momentum is tied to motion, but it is also tied to wavelength, measurement, and symmetry. At ordinary scales, a particle with momentum can be described as having a direction and a tendency to continue moving. In quantum physics, it is also associated with how rapidly its wave-like behavior varies across space. But near the Planck scale, if space itself is no longer smooth, then the usual meaning of wavelength may break down. If time is not a simple background, then the usual meaning of energy evolution may change. If space-time geometry is uncertain, then the usual meaning of a particle travelling through it may be incomplete. Planck momentum is extreme not only because it is large, but because it lives at the boundary where the words used to define momentum begin to depend on the very structure being questioned. Several images have been proposed for what space-time might be like near this boundary. One popular phrase is quantum foam. It suggests that at unimaginably tiny scales, space-time may fluctuate wildly, with geometry bubbling and shifting rather than remaining smooth. The image is helpful if held lightly. It does not mean space is literally made of foam like the top of a bath. It means the smooth geometry of relativity may give way to quantum fluctuations when examined at extremely small scales. Distances, durations, and perhaps even causal order may not be as definite as they are in the larger world. The calm fabric becomes restless. Other approaches imagine discreteness. In some theories, area and volume may come in smallest units, not because space is made of little cubes, but because the measurable geometry has quantum spectra. That means certain geometric quantities may have allowed values rather than any value at all. This is a very different picture from ordinary smooth space. It suggests that below a certain scale, asking for smaller and smaller subdivisions may not correspond to physical reality. Again, this is not settled, it is one possible path. But it shows the kinds of changes physicists consider when the Planck scale appears. String theory offers another kind of change. Instead of point particles, it proposes tiny extended objects whose different vibrations appear as different particles. Because strings have size, they can soften the problems that arise when interactions are squeezed into exact points. In this view, trying to probe shorter distances may reveal not smaller point-like structures, but the extended nature of the fundamental objects. In some cases, increasing energy does not lead straightforwardly to smaller distances, because strings can stretch, vibrate, and behave in ways that alter the old relationship between momentum and resolution. The Planck scale remains central, but the route through it is different. There are also ideas in which spacetime emerges from quantum information or entanglement. In these approaches, space is not the starting point. It is a large-scale pattern that arises from more basic relationships. The distance between things may reflect how quantum systems are connected rather than being a primitive fact. If this is right, then near the Planck scale, the question of what space is becomes even more radical. Motion through space might be an approximate description of changing relationships in a deeper structure. Momentum might also be an emergent or transformed concept, meaningful only once the large-scale space-time pattern has appeared. These possibilities differ, and no final answer has been confirmed. That uncertainty is important. The Planck scale is not a place where we can confidently describe a tiny landscape with miniature clocks and rulers. It is a frontier where multiple serious theories attempt to explain why the familiar world works so well, while also avoiding contradictions at the deepest level. What unites these theories is the expectation that ordinary space-time cannot simply be assumed forever. Something has to give, or at least something has to be explained more deeply. The difficulty of testing Planck scale physics is enormous. The energies needed to directly probe such distances are far beyond present particle accelerators. The gap is so large that it is not merely a matter of improving engineering. It is a sign that direct access may be physically limited in principle. So scientists look for indirect signs. They study black holes, the early universe, gravitational waves, high-energy cosmic particles, and the mathematical consistency of theories. They ask whether Planck scale effects might leave tiny traces in light travelling across the cosmos, in the patterns of the cosmic microwave background, or in the behaviour of black hole radiation. So far, the clues are incomplete. The Planck scale remains mostly hidden, not because it is unimportant, but because it is so deeply buried beneath ordinary scales of experience. This hiddenness can make the Planck scale feel almost unreal, but it is not a fantasy. It is a logical meeting point of established ideas. Quantum theory is real and tested. Relativity is real and tested. Gravity is real and tested. The constants that define their scales are measured features of nature. When combined, they point toward Planck quantities. The uncertainty lies not in whether the Planck scale is meaningful, but in what exactly happens there. It is like seeing smoke beyond a hill. You may not know the shape of the fire, but the smoke is a sign that something is there. The loss of usual meaning at the Planck scale also teaches us something about the nature of scientific concepts. Words like space, time, particle, and momentum are not sacred objects. They are tools. They work because they describe patterns reliably within certain domains. At walking speeds and ordinary sizes, Newtonian space and time work well. At high speeds and strong gravity, relativistic spacetime works better. At atomic scales, quantum states and probabilities work better. At the Planck scale, we may need new tools. This does not make the old tools wrong, it places them. A kitchen clock is not wrong because it cannot measure the Planck time. A road map is not wrong because it cannot show molecules in the asphalt. The tool is valid within its range. That can be a soothing thought. Physics does not usually destroy earlier understanding. It surrounds it with deeper understanding. Newtonian mechanics still guides bridges, vehicles, sports, and everyday engineering. Relativity did not erase it. Quantum mechanics did not make tables vanish into mystery. The Planck scale will not make ordinary space and time meaningless at human scale. Your room will remain a room. Your blanket will remain a blanket. Your cup will remain regrettably easy to knock over in the dark. What changes is our belief that the concepts working so well here must continue unchanged forever. At the Planck scale, smoothness may be an approximation. Continuity may be a large-scale appearance. Motion may be a simplified story. Momentum may not be endlessly sharpened. Time may not tick in the background. Space may not wait passively for things to happen inside it. The deep structure could be discrete, extended, relational, foamy, holographic, or something no current image captures. The honest answer is that we do not know yet. But the pressure toward a new idea is strong because the known theories point there from different directions. Planck momentum sits right in the center of that pressure. It is the momentum scale associated with probing the smallest meaningful distances. But if those distances are not ordinary distances, then Planck momentum is not just a large quantity. It is a sign that the relationship between motion and geometry has become unstable. A particle with such momentum cannot be imagined simply as a faster version of a familiar object. It belongs to a regime where the particle may disturb space-time, where black hole-like behavior may appear, where quantum uncertainty affects geometry, and where the usual distinction between the thing moving and the space it moves through may blur. This is why the phrase where space, time, and motion lose their usual meaning is not merely dramatic. It is a practical statement about the limits of our concepts. Space loses its usual meaning because distances may not be divisible or measurable without limit. Time loses its usual meaning because the smooth ordering of moments may depend on a classical geometry that no longer exists in the same way. Motion loses its usual meaning because motion requires a background of space and time, and that background may itself be quantum, fluctuating, or emergent. Momentum loses its usual meaning because it is tied to all three. Even so, the Planck scale is not a place of pure confusion. It is also a place of order waiting to be understood. The fact that the same scale emerges from combining quantum theory, gravity, and relativity suggests that the unknown is not random. It has structure, it has a boundary, it has clues. The universe has not left us with nothing. It has left us with a set of signposts, and Planck momentum is one of them. It tells us where the familiar road becomes unfamiliar. It does not yet tell us what the new road is made of. For now, we can keep the picture simple. At large scales, space is smooth, time flows well enough, and motion can be described clearly. At quantum scales, particles become wave-like and uncertain, but space-time can usually still be treated as a background. At gravitational scales, space-time bends, but quantum effects can often be ignored. At the Planck scale, neither simplification is safe. Quantum uncertainty and gravitational curvature meet. The small and the strong become the same problem. This is why Planck momentum is not just another entry in a list of large quantities. It is the sign of a crossing point, the place where pushing motion to its deepest limit forces us to question the stage, the clock, and the path all at once. And once that is clear, a natural curiosity begins to form. If Planck momentum marks such an extreme boundary, could anything ever actually reach it? Could a particle in the early universe have carried it? Could a black hole create it? Could a future civilization produce it? Or is it less like a destination and more like the horizon of a theory, always telling us where the familiar view ends while keeping the deeper landscape just out of reach? The question of whether anything could ever reach Planck momentum sounds at first like a question about engineering. Could we build a machine powerful enough? Could nature build one where we cannot? Could a future civilization, perhaps with more patience and a less nervous electrical grid, accelerate a particle until it arrives at that extraordinary threshold? It is easy to picture Planck momentum as a distant finish line on a cosmic racetrack, with particles rushing toward it while physicists lean over the barrier holding clipboards. But the more carefully we think about it, the less it looks like a finish line, and the more it looks like a change in the rules of racing. To ask whether anything can reach Planck momentum, we first have to ask what kind of thing we mean. A whole planet can have a huge amount of momentum depending on how it is moving relative to an observer. A star has more. A galaxy drifting through the universe can carry a staggering total momentum if viewed from another moving frame. But that is not the kind of Planck momentum question that usually matters in quantum gravity. Large objects can carry large total momentum because they contain enormous amounts of matter spread across enormous volumes. Their momentum is distributed. It does not all belong to a single tiny probe attempting to examine the smallest possible distance. The Planck momentum question is about momentum concentrated in a very small system or involved in a very sharp interaction. It is about a single particle like excitation, or a collision, or a momentum transfer so intense that it tries to speak directly to the structure of spacetime. This distinction matters because otherwise the answer becomes misleadingly easy. Could something have more total momentum than Planck momentum? In a broad everyday sense, yes, many large moving objects can be assigned momenta far beyond that scale depending on the observer. But could a single particle or localized process reach Planck momentum in a way that lets it remain an ordinary particle moving through ordinary smooth space? That is much less clear. Near that scale, the words ordinary particle and ordinary smooth space begin to look tired. The question shifts from can we give it that much momentum to what would it become if we tried? Human technology is nowhere close. Our greatest particle accelerators are magnificent machines, circular cathedrals of magnets and vacuum pipes and patient measurement, but they operate at energies vastly below the Planck scale for individual particles. They can reveal the deep workings of the quantum fields we know, produce heavy particles, test the standard model, and search for signs of new physics. But compared with the Planck scale, even these machines are gentle. That is not an insult. It is simply the size of the gap. To reach Planck momentum directly with anything like present accelerator methods would require an absurd extension of energy, size, and control. It would not be a matter of making the machine a little larger or increasing the budget with a hopeful smile. It would be a leap across a gulf so wide that ordinary engineering language begins to lose its usefulness. There are natural accelerators in the universe that dwarf our laboratories. Cosmic rays arrive from space with astonishing energies. Some have struck Earth's atmosphere carrying far more energy than particles in our accelerators. Their origins can involve violent astrophysical environments such as supernova remnants, active galactic nuclei, jets near black holes, or other powerful cosmic engines. These particles are reminders that nature can build machines larger and stranger than anything we can construct under a city. Yet even the most energetic cosmic rays known remain far below the Planck scale. They are extraordinary by human standards, but not Planckian by the standards of quantum gravity. The universe throws very fast stones, but apparently not stones sharp enough to knock directly on that deepest door, at least not in any event we have clearly observed. The early universe is a more serious candidate. If anything ever approached Planck momentum in a physically meaningful way, the earliest moments after the beginning of cosmic expansion are among the first places to look. At extremely early times, the universe was hot, dense, and energetic beyond anything found today in ordinary space. The distinctions we now rely on may have been blurred. Particles, if that word even applies cleanly that early, would have been interacting in conditions where quantum gravity may have mattered. The Planck scale is often treated as the point before which our established theories cannot confidently describe the universe, not because nothing happened, but because our current maps do not reach back that far without tearing. In that earliest regime, Planck momentum may not have been something a lone particle reached in the familiar sense. The whole environment may have been Planckian. Space, time, energy, and geometry may have been tangled together in a way that does not resemble particles flying through a pre-existing arena. If we imagine a single particle with Planck momentum, we may already be importing too much later universe thinking into a place where the concept of a particle might not yet be well formed. It is like asking what the weather was like before there was an atmosphere. The question has a shape we understand, but the conditions may not support the words. Black holes offer another possible route. Near a black hole, gravity becomes extreme. Near the horizon of a large black hole, an infalling observer might not notice anything locally dramatic at the crossing, but from the perspective of distant descriptions, energies and frequencies can become highly distorted. Near the centre, where classical general relativity predicts a singularity, curvature grows without bound. Most physicists suspect that the singularity is not a real physical point of infinite density, but a signal that the classical theory has been pushed beyond its proper range. A theory of quantum gravity should replace that infinite prediction with something finite and meaningful. If Planck scale momenta appear anywhere in black hole physics, it would be in these deep quantum gravitational regions, or in the processes connected with black hole evaporation and the final stages of tiny black holes. But again, the language must be cautious. A black hole can have a large total momentum if it moves through space. That is not the same as saying something inside or near it has Planck momentum in the clean particle sense. Near a singularity, the very idea of a local particle momentum may break down because spacetime itself is no longer described reliably by classical geometry. In Hawking radiation, particles can emerge from quantum effects near the horizon, but for large black holes the individual radiation quanta are typically very low energy. Only for extremely tiny black holes would the emitted particles become enormously energetic, and as such a black hole approached the Planck scale, our understanding would again require quantum gravity. The Planck regime keeps appearing not as a place where ordinary concepts give straightforward answers, but as the place where those concepts ask to be replaced. Could a future civilization produce Planck momentum? It is tempting to say that given enough time, intelligence, and cosmic real estate, perhaps yes. After all, human history has repeatedly underestimated future technology. Stone tools became steam engines became particle accelerators and space telescopes. It is wise not to assume that our present limitations define all possible engineering. A civilization able to harness stellar or galactic resources might build accelerators of unimaginable scale. It might use black holes, magnetic fields, plasma structures, or mechanisms we would barely recognize. Science fiction has room to play here, and it should. Imagination is one of the gentler engines of curiosity. Yet even granting extraordinary future technology, Planck momentum may not be reachable as an ordinary experimental target. The problem is not just providing energy. It is localizing it without the experiment becoming gravitationally self-defeating. If a device tries to concentrate Planck-scale momentum into a region small enough to probe Planck-length distances, the energy involved may create a tiny black hole or some other quantum gravitational state. The machine may succeed only in demonstrating that the old way of asking the question fails. It could create the threshold, perhaps, but what it creates may not be a particle with a neat label. It may be a short-lived quantum gravitational object, a horizon, a burst of radiation, or something described only by a theory we do not yet have. This is why reaching Planck momentum is different from reaching a high speed. A massive object can approach the speed of light, though never reach it, and relativity tells us how its energy and momentum behave along the way. The speed limit is clear. Planck momentum is not simply another version of that story. It is a scale where the combination of quantum mechanics and gravity becomes unavoidable. Trying to reach it may not produce a clean observation of a particle at that momentum. It may produce a transition into a different physical regime. The question becomes less like asking whether a runner can cross a finish line, and more like asking whether a ship can sail to the place where the sea becomes sky. Something may be there, but the categories have changed. There is also the issue of reference frames. In relativity, different observers can assign different momentum to the same object. If you move rapidly relative to a particle, you may describe it as having very high momentum. This means that, in ordinary relativity, one can make the momentum of an object appear arbitrarily large by choosing a sufficiently boosted frame. But that does not mean one has created a Planck-scale physical interaction. The local physics experienced by the object has not necessarily changed just because an observer describes it differently. What matters for quantum gravity is not merely a coordinate description, but the invariant physical content of an interaction, such as how much energy is concentrated in the collision itself and over what scale. A frame-dependent large momentum is not automatically the same as Planckian local physics. That point prevents a simple trick. One might say, if momentum depends on the observer, then surely any ordinary particle can be viewed from a fast enough frame and called Planck momentum. But this is not the same as reaching Planck momentum in the operational sense. A sleeping cat on a sofa could be assigned a very large momentum by an observer moving extremely fast relative to the house. But the cat does not become a quantum gravity experiment, much to the relief of everyone involved. The meaningful question is whether a process can concentrate Planck-scale energy and momentum in its own physical interaction region. That is where gravity and quantum uncertainty become unavoidable. Observer descriptions matter, but physical thresholds must be handled with greater care than casual frame changing. Some theories do suggest that the Planck scale could be a true invariant limit, not merely a natural scale. In such theories, the transformation rules between observers might be modified so that the Planck energy or Planck momentum plays a role similar to the speed of light, remaining fixed for all observers in some deeper sense. These ideas are explored under various names and motivations. They are attempts to preserve the successes of relativity while adding a second invariant scale related to quantum gravity. If such a theory were correct, then the answer to whether anything could reach Planck momentum might become more definite. It might be impossible to exceed it, or impossible to define momenta beyond it in the usual way. But these ideas remain speculative. They have not replaced standard relativity as established physics. Other theories take a different path. They do not impose a simple maximum momentum, but they prevent unlimited access to small distances through black hole formation, string spreading, discrete geometry, or holographic information bounds. In these views, Planck momentum may be a transition scale rather than a hard ceiling. Objects or interactions above it might exist, but they would not behave like point particles probing smaller lengths. They might behave like larger gravitational states, extended strings, or collective excitations of whatever deeper structure gives rise to space-time. The maximum is then not a ban on larger numbers, but a ban on extending old meanings beyond their proper range. This is a recurring pattern in physics. Nature often does not say no in the way we first expect. It says, not like that. Can you make an object move faster and faster? Yes, but not past the speed of a light if it has mass. Can you cool something lower and lower? Yes, but absolute zero is a limit approached rather than crossed in the ordinary thermodynamic sense. Can you measure smaller and smaller distances with higher and higher momentum? Yes, until gravity and quantum effects change what measurement means. The deepest limits are rarely simple fences, they are changes in the grammar of the world. Could Planck momentum appear in a collision between two cosmic particles? In principle, if two particles collided with enough energy in their centre of mass frame, the interaction could become Planckian. But known cosmic ray events are far below that. Also, even if such an event occurred somewhere in the universe, observing it would be extraordinarily difficult. It might be rare, brief, and hidden behind backgrounds of other astrophysical processes. If it formed a tiny black hole, the signature would depend on quantum gravity. If it produced exotic particles or radiation, those signals might disperse across space long before reaching us. The universe may occasionally stage events more extreme than anything we can see, but science requires evidence, not just possibility. Could Planck momentum exist inside ordinary matter? No, not in any usual sense. The particles inside atoms have momenta far below that scale. Even inside neutron stars, where matter is crushed to extraordinary densities, typical particle energies remain far from Planckian. Neutron stars are extreme by astrophysical standards and deeply important for nuclear physics and gravity, but they are not generally Planck-scale objects throughout their interiors. They may teach us about dense matter, gravitational waves, and the behaviour of matter near collapse, but they are not simple factories for Planck momentum particles. What about the final evaporation of a tiny black hole? This is one of the more plausible places where Planck-scale physics becomes unavoidable. Hawking radiation suggests that black holes slowly lose mass by emitting radiation. Large black holes evaporate incredibly slowly. Tiny black holes would radiate much more strongly. As a black hole shrinks toward the Planck scale, its temperature and emitted quanta would become more extreme, and eventually the semi-classical calculation used by Hawking would no longer be reliable. At that point, a full quantum gravity theory would be needed. The final stage might involve Planck-scale momenta, a stable remnant, complete evaporation, or something else. We do not know. This is another example where the Planck scale marks the edge of current understanding rather than a fully observed process. It is also worth asking whether virtual particles or quantum fluctuations can reach Planck momentum. In quantum field theory, calculations often include contributions from many possible momenta, including extremely high ones. This can lead to infinities that must be handled through renormalization, a powerful and successful procedure. But when gravity is included, very high momentum contributions become more troublesome. This is one reason quantum gravity is difficult. Some approaches suggest that Planck-scale physics naturally cuts off or changes these high momentum contributions. But virtual contributions in calculations are not the same as directly observed particles. They are part of the mathematical structure used to compute physical outcomes. So saying that virtual momenta can be arbitrarily high does not settle whether physical Planck momentum can be reached or exceeded by something measurable. A deeper version of the question asks whether the universe itself allows unlimited momentum in principle. The honest answer is that we do not yet know. Established relativity and quantum field theory, without quantum gravity, allow momentum to grow without a simple, universal cap in many contexts. But those theories are not expected to remain complete at the Planck scale. Quantum gravity may impose a maximum, or it may transform the meaning of momentum, or it may allow larger global values while limiting localized measurements. The phrase maximum momentum possible is therefore best understood as a guiding idea, not a proven final law. It points toward the extreme where possible must be redefined. This does not weaken the wonder of it. If anything, it makes the question more interesting. A simple yes or no would be tidy, but the actual situation reveals how physics thinks. It separates total from localized momentum. It separates observer descriptions from invariant interactions. It separates technological limits from conceptual limits. It separates ordinary particles from quantum gravitational states. Each distinction sharpens the question. By the time we are done, we realise that asking whether anything can reach Planck momentum is really asking whether the universe permits a familiar kind of object to carry that much localised motion without becoming something unfamiliar. If we had to answer in the calmest, careful way, we might say this. Large systems can have total momenta exceeding the Planck momentum in ordinary descriptions. Individual known particles and laboratory processes do not come remotely close. Natural cosmic particles, though far more energetic than our accelerators, still fall far short. The early universe and black hole endpoints are the most likely places where Planck-scale momenta, or related quantum gravitational conditions, could have mattered. But in those regimes, the familiar idea of a particle reaching a momentum may break down. Planck momentum is less a destination for ordinary matter and more a threshold where ordinary descriptions give way. There is a pleasing humility in that answer. It does not pretend we know more than we do. It also does not throw away the clue. Planck momentum remains one of the most meaningful scales in theoretical physics, because it tells us where the known laws begin to overlap in a way that demands a deeper theory. Whether anything reaches it as a particle, whether it acts as a hard maximum, whether it marks a transition into black hole-like behaviour, or whether it is replaced by some deeper concept, it remains a signpost. It tells us that motion cannot be pushed to its most extreme form without asking what space and time are. For the imagination, this is more satisfying than a simple machine reaching a number. It means that Planck momentum is not merely a record to be broken. It is a question the universe asks back. If you push a particle gently, it moves. Push it harder, it moves faster. Push it near the speed of light, its momentum grows while its speed approaches a limit. Push the idea further into smaller distances, and quantum rules sharpen the probe. Push it to the Planck scale and gravity enters with a horizon in one hand and a warning in the other. At that point, the question is no longer just how fast, how hard, or how much. It is what kind of reality allows motion at all. So could anything ever reach Planck momentum? Perhaps in the earliest universe, but not in a form we can describe with ordinary particle language. Perhaps in the last breath of a tiny black hole, though we do not yet know how that story ends. Perhaps in future theories it will be a true upper limit. Perhaps it will be a transition into a different description, where momentum is no longer the right word. What seems unlikely is that it is simply another milestone waiting for a better accelerator and a triumphant press release. The Planck scale is more private than that. It does not offer itself as the next routine step. It waits at the edge where our clearest ideas begin to blur. And that brings us close to the final meaning of Planck momentum. It is not valuable only because it might be reached, exceeded, or forbidden. It is valuable because it shows us that even motion has a horizon of understanding. Momentum begins as something felt in the hands, in carts, stones, waves, and collisions. It grows into a conserved quantity tied to the symmetry of space. It becomes quantum, relativistic, and gravitational. Then, at the Planck scale, it stops being merely a property and becomes a boundary marker. The last step is to ask what that boundary tells us about reality itself, and why the possibility of a maximum momentum, even an uncertain one, may be one of the clearest clues that space, time, matter, and motion are parts of a deeper structure still waiting to be understood. Planck momentum tells us something unusual about reality, because it is not simply another extreme value in a list of extremes. It is not only a very large amount of momentum, it is a marker showing where several of our most successful ideas begin to press against one another. Momentum begins as a simple description of moving things. It tells us why a rolling stone resists being stopped, why a train carries its motion with such seriousness, and why a particle collision can reveal hidden structure. But when momentum is concentrated into smaller and smaller regions, and when that momentum becomes large enough that quantum rules, relativity, and gravity all matter at the same time, it becomes more than a property of motion. It becomes a clue about the limits of the concepts we use to describe the world. The first lesson is that reality is not required to match our everyday categories. We are used to separating things. Matter is one thing, Space is another. Time is the background. Motion is what matter does inside space as time passes. This division works very well for ordinary life. It works for walking, throwing, driving, cooking, building, and most of the physics that keeps bridges standing and satellites in orbit. But Planck momentum points toward a regime where those neat divisions may not survive. A particle with Planck scale momentum would not merely be a small object moving through a passive container. Its energy would affect the geometry around it. The space through which it moves might not remain a silent stage. The act of motion would become tied to the structure of space and time themselves. That is a deep shift. In ordinary thinking, space is where things happen. In general relativity, space and time are part of what happens. They bend, stretch, and respond to mass and energy. In quantum theory, particles and fields do not have all the sharp properties our everyday imagination expects. They're governed by uncertainty, probability, and discrete interactions. Planck momentum is where these two great revisions meet. It asks what motion means when the moving thing is quantum and the arena of motion is gravitational. It asks whether we can still speak of a particle with a definite momentum in a definite place, if the energy needed to define that situation curves the place itself. The question does not merely add difficulty, it changes the subject. This is why the idea of a quiet boundary is useful. Planck momentum does not shout. We do not encounter it directly in ordinary experiments. It does not appear in daily life, in engines, in storms, or in the movement of planets in any simple way. Yet it sits quietly inside the structure of physical law, waiting at the point where our theories suggest they can no longer be used separately. It is quiet because it is far away from experience. It is a boundary because it marks the edge of familiar meaning. On one side, momentum behaves in ways we can calculate, measure, and test with great success. On the other side, we suspect that the words we rely on may have to be rebuilt. One thing Planck momentum tells us is that measurement has limits that are not merely practical. In many areas of science, limitations come from technology. Our instruments are not sensitive enough. Our machines are not powerful enough. Our detectors are too noisy. Those limits can improve with time, but the Planck scale suggests a deeper kind of limit. If we try to measure smaller distances by using higher momentum probes, the probes themselves eventually carry enough energy to disturb the region gravitationally. The measurement process becomes part of the thing being measured. More power does not simply give more clarity. At some point it may create a horizon, or a quantum gravitational state, or a disturbance of spacetime so strong that the old idea of looking more closely no longer works. This is a humbling message. It means that nature may not be infinitely open to the same method of questioning. The method that worked so well for discovering atoms, nuclei, and quarks may not continue without change forever. Higher momentum has served as a sharper tool, but a tool can become too disruptive for the task. Near Planck momentum, the tool may become the event. The probe may no longer reveal a smaller object behind the curtain. It may create a new curtain. This does not mean science ends. It means science must change its language. Another lesson is that smallness and largeness are not opposites in the simple way we imagine. Planck momentum belongs to the study of the smallest distances, but it also brings in black holes, which we usually imagine as massive cosmic objects. The smallest scale and the strongest gravity meet. Try to examine a tiny enough region with enough momentum, and the physics begins to resemble the physics of horizons. The very small becomes connected to the gravitationally extreme. That connection is one of the most important clues in modern theoretical physics. It suggests that the deeper structure of matter cannot be understood apart from the deeper structure of space-time. This connection also changes how we think about reality as information. Black holes taught physicists that information, entropy, area, and gravity are linked in surprising ways. The amount of information associated with a black hole is related to the area of its horizon, not simply to the volume inside in the ordinary way. That lesson has inspired the idea that the information contained in a region may be limited by its boundary. If this is true in some deeper form, then the world may not be built from unlimited independent details at arbitrarily small distances. Planck momentum fits into this idea because it marks the scale where trying to encode or reveal still finer details may run into gravitational limits. Reality may have a maximum density of meaningful information, not because imagination fails, but because gravity and quantum theory together set the rules. There is a strong temptation to picture this as space being made of tiny blocks. That might be true in some form, but we should be careful. The Planck scale does not prove that space is a grid of little cubes. It tells us that our smooth description of space is expected to fail or require modification. The deeper structure could be discrete, but it might also be extended, relational, holographic, or something we do not yet know how to picture. Planck momentum is not evidence for one simple image. It is evidence that simple images are probably not enough. Reality may not be made of smaller versions of familiar things. It may be organized in a way that only becomes familiar after we've learned the right concepts. That has happened before. Atoms were once imagined as tiny hard spheres. That image was useful for a while, but it did not survive the rise of quantum mechanics. Electrons are not little planets circling a nucleus in neat tracks. Light is not only a wave or only a particle in the everyday sense. Time is not a universal clock shared by all observers. Again and again, physics has shown that familiar pictures work within their range and then fail at the edges. Planck momentum may be another edge. It warns us not to expect the deepest level of reality to look like a smaller version of the world we already know. It also tells us that motion is not as simple as displacement through emptiness. In classical physics, motion is usually pictured as an object changing position over time. In relativity, motion depends on the observer, and energy and momentum are woven into spacetime. In quantum theory, momentum is tied to wavelength and uncertainty. Near the Planck scale, motion may be linked to the quantum state of geometry itself. A thing cannot simply move through spacetime if spacetime is fluctuating, emergent or not sharply defined. The background and the motion may have to be described together. This is a difficult idea, but it is also a coherent one. If spacetime is not fundamental, then motion through spacetime cannot be fundamental either. It must arise from something deeper. That possibility is one reason Planck momentum matters, even though we cannot reach it directly. It is a signpost pointing toward emergence. Many things in nature are real without being fundamental. Temperature is real. You can feel heat and cold. You can measure temperature. It affects chemistry, weather, biology, and comfort. But temperature is not a property of a single molecule in the ordinary thermodynamic sense. It emerges from the collective behavior of many particles. Sound is real, but it emerges from vibrations moving through a medium. A wave on the ocean is real, but it is not a separate substance from the water. In a similar way, space, time, and momentum as we know them may emerge from deeper relationships. Planck momentum may be where that emergence begins to show its seams. The word reality can feel too large, so it helps to bring the idea back to a practical statement. Our current reality description works in layers. For everyday motion, classical mechanics is usually enough. For fast motion and gravity, relativity is needed. For atoms and particles, quantum theory is needed. For high-energy particles without strong gravity, quantum field theory works extremely well. But if we combine tiny distances with enormous momentum, gravity and quantum theory must both be present. That is the layer we do not yet fully possess. Planck momentum tells us where that missing layer should matter. This makes it a boundary of knowledge, not a boundary of curiosity. There is no shame in reaching such a boundary. Boundaries are how science learns where to look next. The ultraviolet catastrophe showed where classical physics failed and quantum theory began. The strange constancy of light speed showed where Newtonian time and space failed and relativity began. The behavior of atoms showed where classical orbits failed and quantum states began. Planck momentum may be showing us where quantum field theory on smooth space-time and classical gravity Both fail as separate descriptions. The failure is not defeat. It is a clue with very good manners, standing quietly at the edge of the map. We should also notice what Planck momentum does not tell us. It does not give a completed theory of quantum gravity. It does not prove that momentum is strictly capped for every observer. It does not show that space is definitely discrete. It does not tell us exactly what happened at the first moment of the universe or at the final stage of black hole evaporation. A good scientific idea does not have to answer everything to be valuable. Sometimes its value lies in asking the right question with enough precision that vague mystery becomes structured mystery. Planck momentum does that. It gathers several uncertainties into one focused place. There is a calm honesty in saying that we do not know the final answer. Physics is sometimes presented as a collection of finished facts, but at its best it is also a map of what remains unfinished. The unfinished parts are not empty. They are shaped by what we already know. Planck momentum is not random speculation. It is built from the constants and theories that have survived severe tests. Quantum theory works, relativity works, gravity works. Their overlap points toward trouble. That trouble is meaningful because it comes from success. Our theories are so powerful that they can tell us where they expect themselves to become incomplete. This is one of the more beautiful features of science, though not beautiful in a decorative way. A good theory contains its own horizon. It describes a domain so well that we can see the outline of the next domain beyond it. Planck momentum is part of that outline. It does not tell us what the deeper theory will be, but it tells us that any deeper theory must explain why Planck scale momentum is special. It must explain how quantum uncertainty, gravity, energy, and space-time fit together. It must explain why the familiar world emerges so smoothly from whatever happens there. That last requirement is important. A theory of the Planck scale must not only handle extremes, it must also return us to ordinary life. It must explain why chairs, clocks, planets, atoms, and sleepy listeners behave as they do. In that sense, Planck momentum connects the farthest abstraction to the nearest experience. You do not feel Planck momentum when you move your hand, but the same universe that permits your hand to move also contains the laws that point to Planck momentum. The same idea of momentum that lets a ball roll across a floor leads, when followed with enough care, to questions about black holes and quantum spacetime. That continuity is one of the reasons physics can be reassuring. The strange is not separate from the ordinary. It grows out of the ordinary when the ordinary is pushed far enough. Planck momentum also teaches restraint. It tells us not to assume that because a mathematical quantity can be extended, the physical meaning can follow without change. We can write about smaller distances and larger momenta in familiar language, but nature may not provide a process that realizes those words in the same way. Physical meaning depends on what can exist, interact, be measured, and remain coherent within the laws. At the Planck scale, the familiar meanings may be transformed. That is not a failure of imagination. It is a reminder that reality is not obligated to preserve our grammar. Still, the boundary is quiet rather than hostile. It does not forbid thought. It invites better thought. It invites theories that make space and time quantum without destroying their successful large-scale behavior. It invites new views of black holes that preserve information and explain horizons. It invites a deeper understanding of measurement, locality, and causality. It invites us to ask whether momentum is fundamental or whether it is a large-scale expression of something more basic. These are not small questions, but they are not meaningless. They are guided by Planck momentum and its neighbouring Planck quantities. As the whole journey settles, the meaning becomes clearer. Momentum began as the carried insistence of motion. A moving object resists being stopped because motion has a kind of physical commitment. That idea became a conserved quantity, protected by the sameness of space. It expanded through relativity, where energy and momentum became inseparable parts of a deeper structure. It entered quantum theory, where momentum is tied to wavelength, uncertainty, and the ability to probe small distances. It met gravity, where energy and momentum curve space-time. Finally, at Planck momentum, all these threads tighten into a boundary. Not the end of physics, but the end of a certain confidence. That boundary tells us that reality is layered, and that each layer has rules that may not survive unchanged at the next. It tells us that space and time may be less basic than they appear. It tells us that motion may not be a simple, primitive fact. It tells us that measurement has physical consequences that cannot always be made small. It tells us that the universe may protect its deepest structure not by hiding it arbitrarily, but by making the act of unlimited probing impossible within the old concepts. And it tells us that the deepest laws may be less like a machine with smaller and smaller gears, and more like a set of relationships from which gears, machines, space, time, and motion all emerge. For a bedtime thought, that is large but not frightening. The world around you remains steady. The room does not need quantum gravity to be a room. The bed does not require a theory of Planck momentum to support you. The clock can keep ticking in its ordinary way, even if time itself may have deeper secrets. Most of reality at our scale is wonderfully forgiving. The laws that govern the Planck boundary do not disturb the simple comfort of breathing, resting, and listening. They sit far beneath the surface, giving the familiar world a hidden depth. So if Planck momentum is the maximum momentum possible, it is maximum in a careful and profound sense. It is not merely the biggest amount of motion on a scoreboard. It is the scale where localized momentum becomes so extreme that our usual description of motion may stop being meaningful without a deeper theory. It is a boundary between known language and needed language. It is a reminder that the universe can be understood, but not always on the first terms we bring to it. And now, after following momentum from rolling objects to quantum probes, from Max Planck's radiation problem to black holes and the edge of space-time, we return to the quiet place where the idea first becomes personal. Everything around you is moving. The Earth turns, the planet circles the sun moves through the galaxy, particles in the air shift and scatter, light crosses the room, your own breath moves gently in and out. None of this approaches Planck momentum, none of it needs to, but all of it belongs to the same physical story. That may be the most peaceful lesson of all. The greatest extremes in physics are not separate from the ordinary world. They are the far edges of the same laws that let ordinary things happen. Planck momentum waits at an unimaginable boundary, but the path to it begins with every simple motion we know: a tossed pebble, a beam of light, a particle in a detector, a star collapsing into darkness. And the earliest heat of the universe all belong to one connected account of motion and meaning. So wherever you are listening from tonight, and whatever small movements are happening around you, the universe is carrying them with care. Most motion is gentle, some motion is violent. At the deepest edge, motion becomes a question about reality itself, and perhaps that is enough to rest with for now. Not an answer that closes everything, but a boundary that gives the unknown a shape. Planck momentum reminds us that even the most familiar ideas can lead to the edge of understanding if followed patiently. It reminds us that physics is not only about what moves, but about what motion reveals. And in the quiet after such a thought, the ordinary world can feel a little larger, a little stranger, and still perfectly calm. Sleep well, fellow traveller, wherever you are, and wherever your small piece of the moving universe carries you next.